Have you ever gazed up at a clear night sky, far from the city lights, and felt a profound sense of wonder? That feeling, that deep and humbling curiosity, is our gateway to the cosmos. And today, we're traveling to a place so immense, so packed with cosmic drama, it redefines what we think we know about the universe. Picture this, a colossal gathering of galaxies, thousands of them, all bound together by gravity in one of the most spectacular regions of space we've ever observed, the Leo cluster. It's a celestial metropolis, a hub of stellar activity that should, by all our current understanding, be a place of predictable cosmic order. But what if I told you that within this seemingly familiar expanse lie secrets that defy all explanation? What if the very heart of this cluster holds mysteries so profound they challenge the foundations of modern astronomy? Welcome to a journey into the unknown, right here in our cosmic backyard. We're about to dive deep into the Leo cluster, a region that astronomers have studied for decades, yet one that continues to surprise and baffle them with every new observation. Within its vast, swirling depths, we've uncovered 25 distinct phenomena that simply don't add up, from galaxies that move in ways they shouldn't, to energy signatures that appear and vanish without a trace, and gravitational anomalies that hint at forces we have yet to even name. These aren't just minor puzzles, they are gaping holes in our cosmic map, clues pointing to a reality far stranger and more magnificent than we ever imagined. This video is your personal invitation to join that adventure. We'll navigate through these 25 unexplained phenomena one by one, exploring the leading theories, the dead ends that have left scientists scratching their heads, and the thrilling possibilities that lie just beyond our current grasp. This isn't just a list of facts, it's a story of human curiosity pushing against the boundaries of the known. It's about the awe that comes from realizing that the universe is far wilder, more creative, and more mysterious than we ever supposed. So get comfortable, open your mind to the extraordinary, and let's embark on this cosmic detective story together, uncovering the secrets hidden within the magnificent Leo cluster. Our journey into the mysteries of the Leo cluster begins with a discovery so bizarre it sent shockwaves through the astronomical community, a galaxy that seems to be missing its ghost. To understand just how strange this is, we first need to talk about dark matter itself. Think of dark matter as the invisible scaffolding of the universe. We can't see it, taste it, or touch it, but we know it's there because of its immense gravitational pull. Every galaxy we've ever studied, including our own Milky Way, is embedded within a huge, massive halo of this mysterious substance. It's this dark matter that acts like a cosmic glue, holding galaxies together and dictating how they spin and move. Without it, according to all our models, galaxies would simply fly apart. Now, imagine the astonishment when researchers pinpointed a galaxy in the Leo cluster, a perfectly normal-looking collection of stars, and found its gravitational signature was all wrong. The stars within it were moving at speeds that should have torn the galaxy to shreds, yet there it was, intact. The only explanation for such graceful, slow-moving stars was a profound lack of the gravitational anchor that dark matter provides. This galaxy, for all intents and purposes, appears to be running on empty. It's like finding a car speeding down the highway with no engine. The very thing that should be powering its motion is simply gone. This single observation throws a massive wrench into our standard theory of galaxy formation. The prevailing idea has always been that galaxies form within these vast clouds of dark matter. The dark matter clumps together first through gravity, and then its pull attracts the regular, visible gas and dust that eventually condenses to form stars. So, to find a galaxy that formed without this essential ingredient is like finding a castle built without a foundation. It challenges the very sequence of events we thought governed the birth of all cosmic structures. How did this galaxy even come to be? How has it managed to hold itself together over billions of years without flying apart? Scientists have scrambled to propose theories, and the leading ones are as fascinating as the mystery itself. One compelling idea is that this galaxy might be the result of a violent cosmic collision. Picture two galaxies passing through each other in the crowded environment of the cluster. In this chaotic gravitational dance, the dark matter, which doesn't interact with itself or other matter, could have been stripped away, while the regular, colliding gas was compressed and triggered a burst of star formation, creating what looks like a new galaxy born from the wreckage. Another, more radical, theory suggests that dark matter might not be a single, monolithic substance. Perhaps there are different types of dark matter, and this galaxy is made of a variety that interacts in ways we can't yet detect, or perhaps doesn't interact gravitationally in the way we assume. This single, ghostless galaxy in the Leo cluster forces us to confront the limits of our knowledge. It stands as a cosmic rebel, a silent challenge to our most fundamental assumptions. Its very existence is a powerful reminder that the universe is under no obligation to conform to our textbooks, and that sometimes the most profound discoveries come from finding something that simply isn't there. Just as we're grappling with a galaxy missing its fundamental anchor, the Leo cluster presents us with another puzzle of an entirely different scale and nature. Shift your perspective from individual galaxies to the vast, empty-seeming space between them. This intracluster medium is far from a true void. It's a superheated, thin plasma, and within the heart of the Leo cluster, this space itself is screaming. It's emitting a faint but immense whisper in the form of radio waves, a colossal structure known as a giant radio halo. Picture a cloud of energy so vast it could easily encompass thousands of galaxies like our own, a diffuse and mysterious glow that paints the entire central region of the cluster in invisible light. The sheer size of this halo is difficult to comprehend. We're talking about a structure that spans millions of light years, making the cluster itself not just a collection of islands, but a single, connected entity humming with energy. Detecting it requires some of the most sensitive radio telescopes on Earth, instruments that can piece together this faint signal from the cosmic background noise. What they reveal is a smooth, massive veil of synchrotron radiation, a specific type of emission that tells us one thing for certain. There are electrons within that plasma moving at nearly the speed of light, spiraling around magnetic field lines that are woven through the intergalactic space. And this is where the profound mystery begins. We understand the basic mechanism. Ultra-relativistic electrons plus magnetic fields equal radio waves. But what we don't understand is the engine. What cosmic particle accelerator is powerful enough to flood millions of light-years of space with these high-speed electrons? The energy required is staggering, equivalent to the simultaneous explosion of millions of supernovae. According to our standard models, the turbulent energy left over from the cluster's formation should have dissipated over billions of years. The electrons themselves, racing around at such speeds, should lose their energy to radiation over a relatively short time, far too quickly to travel across the entire halo and create such a uniform, widespread glow. So, something must be continuously re-accelerating them, injecting fresh energy into the system to keep this giant radio phantom alive. The leading theory points to colossal mergers, the slow-motion, billion-year collisions of entire galaxy groups within the cluster. The gravitational chaos of such an event could, in theory, stir up the intracluster medium, creating shock waves and turbulence that act like a vast natural particle collider. The problem is, the Leo cluster doesn't show the clear, violent signs of a major recent merger that our models say would be necessary to power a halo of this magnitude. It appears relatively relaxed, a mature cosmic city, not one in the throes of a chaotic urban overhaul. This disconnect forces astronomers to consider even more exotic possibilities. Perhaps the magnetic fields themselves are far more complex and dynamic than we thought, capable of storing and transferring energy in ways we haven't yet imagined. Or maybe there are subtle, continuous processes at work, the gentle sloshing of galactic gas, or the combined output of countless supermassive black holes that collectively provide just enough energy to sustain the halo. The giant radio halo of the Leo cluster is more than just a celestial object. It's a profound question about energy, scale, and the hidden interconnectedness of the cosmos. It shows us that even the apparent emptiness of space is a vibrant, energetic, and deeply puzzling frontier. Now we turn our attention to a different kind of phantom haunting the Leo cluster, not a single missing entity, but an entire population of cosmic ghosts. Scattered throughout this vast assembly are galaxies of an utterly bizarre and paradoxical nature. They are known as ultra-diffuse galaxies, or UDG, and they defy every intuition we have about what a galaxy should look like. Imagine a galaxy the size of our own majestic Milky Way, with its sprawling spiral arms spanning over 100,000 light-years. Now, picture that same immense structure, but instead of containing hundreds of billions of bright, gleaming stars, it holds only a paltry 1% of that number. The result is a ghostly, translucent smudge of light, so faint that for decades it simply melted into the background glow of the universe, completely invisible to our telescopes. The discovery of this specific population in the Leo cluster was a watershed moment, made possible by powerful new instruments and painstaking survey work. Astronomers weren't even looking for them specifically. They were simply mapping the cluster in unprecedented detail when these enormous, whisper-thin structures began to emerge from the data. It was like carefully scanning a crowded, well-lit city square at night and suddenly noticing dozens of ethereal, transparent giants standing motionless among the people, so faint you could see right through them. Finding one such galaxy would have been curious. Finding them to be a common, almost standard feature of the cluster was revolutionary. It revealed an entire hidden dimension to the cluster's makeup, a secret society of giants living in plain sight. Their very existence poses a double-barreled mystery. First, how does something so large and so faint even hold itself together? The crowded environment of a galaxy cluster is a gravitational war zone. As galaxies swing past each other, their immense gravitational pulls act like cosmic wrecking balls, a process known as tidal disruption. Smaller, more fragile galaxies are routinely shredded and torn apart, their stars scattered into the intracluster medium. Yet, these ultra-diffuse galaxies, for all their apparent fragility, show a remarkable resilience. They orbit through this chaotic environment and remain intact. This suggests that, unlike the dark matter-free anomaly we discussed earlier, these UDGs might be absolutely dominated by the stuff. They may, in fact, be so massively overweight with dark matter that its gravitational grip is what shields their sparse stars from being torn away, making them not feeble ghosts but incredibly sturdy, invisible fortresses. This leads directly to the second and even more perplexing part of the puzzle. How did they form? How do you create a structure with the size of a giant but the stellar content of a dwarf? The theories swirling around this question are fiercely debated. One school of thought suggests these are failed galaxies. In this scenario, these UDGs began their lives like any other massive galaxy, accumulating a huge halo of dark matter early in the universe. But for some reason, perhaps because they resided in a region where the intergalactic gas was too hot or had been stripped away early on, the process of converting that gas into stars was brutally inefficient. The galaxy had the raw potential for greatness, but its star-forming engine was starved, leaving it a vast, dark skeleton with only a sprinkling of stellar light. A competing and equally compelling idea involves the violent environment of the cluster itself. Perhaps these galaxies were once more normal, but as they fell into the cluster's intense gravitational well, their gas, the fuel for new stars, was violently ripped away by a process called ram pressure stripping. Picture a galaxy plunging through the superheated intracluster plasma at millions of miles per hour. The resistance is so immense that it acts like a torrential cosmic wind, blowing the galaxy's gas clean out of it. This would instantly quench any ongoing star formation, leaving behind a large but now stagnant system that simply ages and fades, its existing stars spreading out into the diffuse structure we see today. The prevalence of UDGs in the Leo cluster compared to quieter regions of space strongly supports this idea that the cluster itself is the sculptor, creating these phantoms through a relentless billion-year-long assault. This population of cosmic wraiths is more than just a curiosity. It is a crucial piece of the puzzle in understanding how environments shape the evolution of galaxies, forcing us to rewrite the life stories of these most fundamental building blocks of the cosmos. If you thought the ghostly galaxies and the giant radio halo were strange, prepare for a phenomenon that turns our understanding of cosmic weather completely upside down. Within the superheated plasma that fills the space between the Leo cluster's galaxies, astronomers have mapped something that seems to defy the most basic laws of thermodynamics. A colossal, razor-sharp boundary where the searingly hot gas on one side sits directly alongside significantly colder gas on the other, with a temperature drop so abrupt it's like discovering an invisible wall separating a blast furnace from a walk-in freezer. These structures are known as cold fronts, and they are among the most spectacular and puzzling features in the entire cluster. To grasp why this is so shocking, you need to appreciate the normal behavior of a gas, especially one as tenuous and energetic as the intracluster medium. Left to its own devices, heat always flows from a hotter area to a colder one, spreading out evenly until everything reaches the same temperature. It's the same reason a steaming cup of coffee eventually cools to room temperature. The energy disperses. In the vast, seemingly chaotic expanse of a galaxy cluster, you would expect this million-degree plasma to be a churning, well-mixed soup, with temperatures smoothly grading from one region to another. But the cold fronts in the Leo cluster show no such blending. Instead, they present a distinct, sloshing edge that has remained incredibly crisp and well-defined for what was likely billions of years. This isn't a gentle gradient, it's a cosmic cliff face of temperature. So, how does such a stark boundary form, and more importantly, how does it survive? The prevailing explanation is as dramatic as the phenomenon itself, a colossal merger. Picture this not as a direct head-on collision, but as a gargantuan, slow-motion splash. One smaller group of galaxies, with its own envelope of dense, cooler gas, plows into the main body of the Leo cluster. As it does, the denser, cooler core of this incoming group, like a blob of thick syrup dropped into a pot of hot water, sinks toward the center. But the cluster's own hot gas pushes back, creating immense pressure that shears and wraps around the invading core. This gravitational sloshing motion creates these sharp contact discontinuities, the cold fronts where the dense, cold gas of the infalling subgroup rubs up against the hotter, thinner gas of the main cluster. The mystery, however, isn't really in their formation, but in their astounding longevity and precise structure. According to our models, the sheer turbulence and intense heat conduction within the cluster plasma should quickly erode these sharp boundaries. The hot particles on one side of the front should easily cross over and warm up the cold side, blurring the edge into a gentle transition within a relatively short cosmic time frame. Yet the cold fronts in Leo remain knife-edge sharp. This points to a hidden, stabilizing force that is effectively insulating the cold gas from the overwhelming heat surrounding it. The prime suspect is magnetic fields. Astronomers theorize that the sloshing motion of the gas itself may be stretching and amplifying magnetic field lines, weaving them tightly along the surface of the cold front. This magnetic layer could then act as a highly effective shield, a kind of cosmic insulation blanket that prevents the rapid mixing of particles across the boundary, preserving the temperature difference for eons. But the magnetic field theory, while compelling, is not a perfect fit. The required strength and specific configuration of these fields are difficult to reconcile with our broader understanding of cluster physics. It prompts a deeper question. Are we witnessing a standard, if poorly understood, outcome of cluster mergers, or is the Leo cluster showcasing a unique set of conditions that allows these pristine structures to persist? Each cold front is a frozen fossil record of a single, ancient cataclysm, a snapshot of a violent event that occurred billions of years ago. By studying their precise shapes and temperatures, we are essentially reading the history of the cluster's growth, one gravitational upheaval at a time. They are not just thermal anomalies, they are the lasting scars from the cluster's most dramatic collisions, offering us a unique window into the turbulent, high-energy weather systems that govern the largest structures in our universe. Just when we think we've mapped the grand structures of the Leo cluster, it reveals a level of detail even more intricate and telling. If you look closely, you'll find the cluster is crisscrossed with faint cosmic scars, long, wispy ribbons of stars known as galactic streams. These are the ghostly remnants of smaller dwarf galaxies that ventured too close to the cluster's mighty gravitational embrace and were slowly, methodically torn apart over billions of years. It's a natural process, the cosmic equivalent of a spider's web, where the larger structure captures and consumes the smaller. But within the Leo cluster, these streams are not behaving as they should. Their paths are twisted in unexpected ways, and their densities fluctuate strangely, suggesting they are not just passively drifting, they are tracing the outline of something we cannot see. To visualize this, picture our own Milky Way. We observe similar, though much smaller, stellar streams in our galactic halo, formed as our galaxy consumes tiny satellite galaxies. These streams typically follow smooth, predictable orbital paths, their stars flowing along like water in a gentle river. They are the fossil records of past collisions, and by studying their shape, we can reconstruct the history of the merger. In the Leo cluster, however, the streams tell a more chaotic story. Instead of smooth arcs, some appear kinked or warped. Their star density isn't uniform. There are unexpected gaps and clumps along their length, as if the stream has been plucked or disturbed by some invisible hand. This is the core of the anomaly. These streams seem to be interacting with something that isn't there. The most compelling explanation points directly to the hidden architecture of dark matter. Our current models of cosmology predict that large halos of dark matter, like the one enveloping the entire Leo cluster, should themselves be filled with a vast number of smaller dark matter clumps or subhalos. These are the invisible building blocks that merge to form the cluster in the first place. They are the cosmic equivalent of submerged rocks in a river, unseen but capable of disturbing the flow. According to this theory, as a stellar stream passes near one of these dense, invisible subhalos, its intense gravitational pull would tug on the stream, distorting its path and causing stars to bunch up or spread out in ways that leave a distinct signature. The anomalous streams in Leo are therefore not just debris. They are incredibly sensitive gravitational probes reacting to the subtle, unseen mass that permeates the cluster. Yet there's a problem. The number and strength of the distortions we see in some of these streams seem to suggest a population of dark matter subhalos that is richer or more massive than our best simulations predict. It's as if we're seeing more submerged rocks in the river than our maps indicated were possible. This discrepancy opens up a fascinating and deep cosmological debate. One possibility is that our understanding of dark matter itself needs refinement. Perhaps dark matter is colder or warmer than we think, affecting how readily it clumps on small scales. If it's slightly warmer, meaning the particles move faster, it would suppress the formation of these very small subhalos, which would make the streams we see even more difficult to explain. Alternatively, we might be seeing the effects of something else entirely, such as the subtle, cumulative gravitational influence of thousands of entirely dark galaxies, made almost exclusively of dark matter with virtually no stars, whose presence would only be betrayed by their gravitational effect on these visible traces. The implications of solving this mystery are enormous. By reading the subtle warps and clumps in these stellar streams, we are effectively creating a map of the cluster's dark matter substructure in unprecedented detail. It's a new form of astronomy, one that uses the visible to chart the invisible. Every kink is a data point, every density fluctuation a clue. These streams are more than just the ghosts of galaxies past. They are active, dynamic tools allowing us to sense the hidden skeleton of the cosmos. They provide a unique testing ground for the very theories of how dark matter behaves and how the largest structures in the universe assemble themselves. In their silent, graceful orbits, they hold the potential to reveal the fine-grained structure of reality itself. But the Leo cluster's repertoire of oddities doesn't stop at ghostly galaxies or sharp thermal cliffs. It also contains objects that glow with a hidden, warm light, whispering secrets in a part of the spectrum our eyes cannot see. We now arrive at a phenomenon that requires us to look at the universe in a different kind of light, literally. Nestled among the cluster's thousands of galaxies are specific ones that present astronomers with a peculiar energy budget. They emit a tremendous, unexpected surplus of infrared radiation. In simple terms, these galaxies are far warmer and glow much more brightly in infrared than any standard model predicts. It's as if you had a household appliance that, while seeming to function normally, was secretly radiating a massive amount of heat, far more than its power consumption should allow. This luminous infrared excess is a major clue that something significant is happening within these systems, something that standard optical observations completely miss. To understand why this excess is so baffling, we need to consider the cosmic energy cycle of a typical galaxy. Stars are the primary engines, converting hydrogen into helium and releasing vast amounts of energy, mostly as visible and ultraviolet light. Interstellar dust, tiny, sooty particles of carbon and silicon, permeates the galaxy. When starlight hits these dust grains, they absorb that high-energy visible and UV light, heat up, and re-radiate the energy back out as lower-energy, thermal infrared light. It's a straightforward conversion process. The amount of infrared light you detect should, in principle, be directly linked to the amount of visible starlight being absorbed. But in these Leo cluster galaxies, the math doesn't add up. The observed infrared glow is disproportionately high. There simply isn't enough visible starlight to account for all that warmth. This means the primary energy source is hidden from our direct view, shrouded in an immense veil of dust. The most immediate and logical explanation points to a frenzy of hidden star formation. Imagine a galaxy that has recently undergone a massive merger or a sudden influx of gas, triggering the birth of millions of new stars all at once. These newborn stars, especially the most massive and luminous ones, form deep within colossal, dense clouds of gas and dust. These natal cocoons are so thick that virtually all of the brilliant visible light from the new stars is absorbed by the surrounding dust, which then heats up and irradiates the entire energy output of the stellar nursery as infrared light. From the outside, the galaxy might look relatively quiet and mature in visible light, but in the infrared it would be blazing, a sign of a stellar baby boom happening behind the scenes. This is a well-known phase in galaxy evolution, and the intense environments of galaxy clusters can certainly trigger such events. Yet, for some of these Leo cluster galaxies, even the hidden starburst theory falls short. The sheer scale of the infrared excess is so extreme that it would require a rate of star formation so violent and sustained that it would be difficult to hide completely, and it would likely produce other observable signatures that are absent. This forces astronomers to consider a far more titanic and exotic power source, a deeply buried active galactic nucleus, or AN. At the heart of most large galaxies, including our own, lies a supermassive black hole. When such a black hole is actively feeding on surrounding gas and dust, the infalling material forms a searingly hot accretion disk and can launch powerful jets of particles. This process is incredibly efficient at converting mass into energy, often outshining the entire rest of the galaxy. If this central engine is enshrouded in a thick, donut-shaped ring of dust, a structure known as a torus, the accretion disk's intense UV and X-ray light will be absorbed and reprocessed into a tremendous outpouring of infrared radiation. In this scenario, the luminous infrared excess isn't from stars at all, but from the gravitational fury of a feasting supermassive black hole, its brilliance muffled by a cosmic blanket. But the plot thickens even further. What if the dust itself is the source of the mystery? Perhaps the dust in these galaxies isn't the standard interstellar variety we're used to. Could it have different properties, a different composition, or a unique grain-size distribution that makes it extraordinarily efficient at absorbing and re-radiating light? Or maybe the dust is distributed in an unusual geometry, perhaps in a vast, smooth shell that envelops the entire galaxy, allowing it to capture a much larger fraction of the starlight than in a typical spiral galaxy where dust is confined to lanes. While these are plausible ideas, fine-tuning dust properties to explain the most extreme cases often feels like a stretch, pushing the limits of known astrophysical materials. This leads to the most speculative and thrilling of the potential explanations: a population of primordial black holes. These aren't the supermassive giants at galactic centers, but hypothetical black holes that could have formed in the incredibly dense, hot conditions of the very early universe before stars and galaxies even existed. They could range in mass from tiny, asteroid-sized objects to others many times the mass of our Sun. The theory suggests that a galaxy could be swarming with countless such primordial black holes. As they move through clouds of interstellar gas and dust, their immense gravity would pull material toward them. This gas would compress and heat up as it falls in, glowing brightly before vanishing behind the event horizon. While an individual primordial black hole would be faint, the collective glow from millions or billions of them, all subtly heating the surrounding dust, could potentially produce a diffuse, pervasive infrared excess that is difficult to attribute to any single point-like source. This idea remains highly theoretical, but its potential implications are staggering, as it could simultaneously solve the mystery of the infrared excess and provide a major candidate for the universe's missing dark matter. So, the luminous infrared excess in the Leo cluster is far more than a simple anomaly. It is a cosmic diagnostic tool. It forces us to ask a fundamental question: what is the dominant engine shaping this galaxy's evolution? Is it a burst of new life in the form of hidden stars, the destructive power of a central black hole, or the subtle glow from a hidden population of ancient cosmic relics? Each answer paints a dramatically different picture of the forces at work within these island universes, reminding us that the true nature of a galaxy often lies not in the light it emits, but in the heat it keeps. It's one thing to find galaxies that are strangely faint or unexpectedly warm, but the Leo cluster has an even more dynamic puzzle in store: galaxies that appear to be fleeing the scene at impossible speeds. Picture a vast, gravitationally bound system like the Leo cluster as a kind of cosmic metropolis. Just as cars on a highway have a range of speeds but generally stay within the legal limit, galaxies in a cluster orbit with velocities governed by the cluster's total mass, the combined pull of all its visible stars, hot gas, and most importantly, its immense halo of dark matter. This gravitational grip sets a cosmic speed limit. Now, astronomers have identified specific galaxies within Leo whose measured velocities are so extraordinarily high that they seem to be on the verge of escaping the cluster altogether, moving too fast for the cluster's gravity to hold them. This is the mystery of high-velocity galaxy ejections, and it strikes right at the heart of our understanding of gravitational physics on the largest scales. The fundamental question is a simple one. What could possibly give a galaxy, an object containing hundreds of billions of stars, such a tremendous kick? The first and most conventional place to look is gravitational interactions. Within a dense cluster, galaxies can swing past each other in a complex gravitational dance. In a three-body interaction, it's theoretically possible for one galaxy to be slung away at high speed while the other two slow down, a process similar to a gravitational slingshot we use to propel space probes around our solar system. However, for a galaxy to reach the extreme velocities observed, the energies involved are staggering. The other galaxies in the interaction would need to be exceptionally massive, and the encounter would need to be perfectly aligned, a set of conditions so specific and rare that it struggles to account for the number of these high-speed outliers we see. It's as if we found not one, but several cars on our city highway traveling at rocket speeds. A simple explanation like a steep hill or a strong tailwind starts to feel inadequate. This failure of conventional gravity leads scientists to ponder far more exotic possibilities. One of the most profound is the potential influence of dark energy. We typically think of dark energy as the force responsible for the accelerating expansion of the universe on the very largest scales, acting as a kind of anti-gravity that pushes space itself apart. Its effects are usually only noticeable in the vast, empty voids between galaxy clusters. But what if, under certain conditions, dark energy could become more concentrated or its influence could be amplified within a massive structure like the Leo cluster? Could it be providing a repulsive push on specific galaxies, aiding their high-speed escape? While there is no accepted mechanism for this in current physics, the observation forces us to ask whether our understanding of dark energy is truly complete. Perhaps it can interact with the dense environments of clusters in ways we haven't yet imagined, making it a local actor in cosmic dynamics, not just a global force. Another tantalizing and equally powerful explanation involves the most energetic engines in the known universe, supermassive black holes. When two galaxies merge, their central supermassive black holes eventually sink to the center of the new galaxy and can form a binary pair. As they spiral inwards, they can emit gravitational waves, but if the merger is messy and asymmetrical, the final, single black hole can receive a colossal recoil. Think of it like firing a rifle. The bullet shoots forward and the gun kicks back into your shoulder. In this cosmic analogy, the bullet is a blast of gravitational waves, and the gun is the newly merged supermassive black hole. If the kick is powerful enough, it could physically eject the black hole from its host galaxy at a significant fraction of the speed of light. But what we're talking about here is even more extreme. The possibility that the recoil is so immense that it doesn't just eject the black hole, but drags the entire galaxy along with it. For this to happen, the black hole would need to be gravitationally coupled to the galaxy's core for a long time, transferring its incredible momentum to the surrounding stars and gas. While this is considered a fringe scenario, the sheer energy output of these monsters makes it a possibility that cannot be entirely dismissed. Before we get too carried away with cosmic recoils and dark energy pushes, we must rigorously confront a more mundane but critically important alternative. What if we are simply measuring these velocities wrong? Determining the precise speed of a galaxy is a complex process. It relies on measuring the redshift of its light, the stretching of its light waves as it moves away from us. This seems straightforward, but several effects can contaminate this measurement. The first is the peculiar motion of the galaxy within the cluster, which is what we're trying to measure, superimposed on the overall Hubble flow of the expanding universe. Astronomers have sophisticated models to disentangle this, but they are not perfect. More subtly, the immense gravitational field of the cluster itself causes an effect known as gravitational redshift, where light struggling to climb out of the cluster's deep potential well loses energy and is redshifted, mimicking a Doppler velocity. If not accounted for with absolute precision, this could make a galaxy appear to be moving faster than it truly is. Furthermore, if a galaxy is not a single, coherent object but is instead in the process of being tidally stretched or is a projection of two separate systems along our line of sight, our velocity measurement could be a misleading average or a complete misinterpretation of the data. Each of these explanations, from gravitational slingshots to black hole recoils, from dark energy influences to measurement errors, carries its own set of implications and challenges. The high-velocity galaxies in the Leo cluster act as extreme physics laboratories. If they are the product of gravitational interactions, they force us to refine our models of orbital dynamics in dense environments. If they are signs of black hole recoils, they provide a unique window into the violent final moments of galactic mergers. And if they point to a role for dark energy within clusters, they could revolutionize our understanding of the universe's most dominant, yet least understood component. Until we can definitively rule out measurement issues, a healthy skepticism is essential. But the very existence of these cosmic speedsters ensures they remain one of the most compelling and active mysteries in modern astrophysics, pushing our models to their breaking point. Leaving behind the high-speed drama of escaping galaxies, we descend into the very atmosphere of the Leo cluster itself, where an even more delicate and intricate mystery unfolds. Suspended within the superheated plasma of the intracluster medium are vast, ethereal structures known as coronal gas filaments. Picture these not as solid ropes, but as immense, shimmering threads of million-degree gas, weaving through the darkness between galaxies like the delicate, glowing strands of a cosmic spider's web. Some of these filaments stretch for tens of thousands of light years, yet they are incredibly tenuous, far more diffuse than the best vacuum we can create on Earth. Their existence is a marvel of cosmic engineering, and their persistence is a direct challenge to our understanding of how energy behaves in the most extreme environments. The first question is one of origin. How does such a hot, thin gas get organized into these long, coherent threads? The leading theory points once again to the colossal gravitational turmoil of cluster mergers. When two subclusters collide, they don't just pass through each other like ghosts. Their gaseous atmospheres slam together, creating immense shock waves and stirring up incredible turbulence. Imagine two weather fronts colliding in our own atmosphere, generating swirling tornadoes and twisting cyclones. On the scale of a galaxy cluster, this turbulence can stretch and shear the plasma, drawing it out into these long, filamentary structures. It's a natural consequence of chaotic motion, much like pulling taffy into thin strings. However, the problem isn't just their formation, but their astonishing longevity. In a seething, turbulent plasma, these delicate filaments should be shredded and dissolved by surrounding forces in a relatively short time, cosmically speaking. The fact that we see them at all, and in such fine detail, means something must be actively holding them together against the relentless forces of disruption. This is where the mystery deepens considerably. The primary suspect for this stabilizing force is, as with the cold fronts, magnetic fields. But here, the role of magnetism becomes even more critical and puzzling. The prevailing hypothesis is that the turbulent motions that create the filaments also amplify weak, primordial magnetic fields that have existed since the cluster's infancy. As the plasma is stretched, these magnetic field lines are pulled tight and aligned along the length of the filament, effectively creating a magnetic skeleton inside the thread of hot gas. This invisible backbone could provide the structural integrity needed to resist the turbulent forces that would otherwise tear the filament apart. It would act as a conduit, channeling the gas and confining it, preventing it from simply diffusing back into the surrounding chaos. It's a beautiful idea, but it requires the magnetic fields to be both incredibly strong and exquisitely organized on a vast scale, pushing the limits of what we believe is possible. The second major puzzle is the filament's temperature. How are these isolated strands of gas maintained at millions of degrees? The hot plasma should be rapidly cooling down. As the electrons in the gas radiate energy, they should lose heat and the filaments should condense and fade away. Yet they continue to glow brightly in X-ray observations. This points to a continuous local heating mechanism. One fascinating possibility is that the magnetic fields themselves are not just passive scaffolding, they might be dynamic energy conduits. Waves and vibrations could be traveling along these magnetic field lines, much like sound waves traveling along a guitar string. As these waves dissipate their energy within the filament, they could be continually reheating the gas, providing just enough energy input to offset the radiative losses and keep the filament shining. Another source of heat could be cosmic rays, high-energy particles accelerated by shock waves or black holes that diffuse into the filaments and deposit their energy there. However, the standard models of turbulence and magnetic confinement struggle to fully account for the fine, hair-like sharpness and the sheer number of filaments we observe. This has prompted scientists to consider even more exotic ideas. Perhaps we are witnessing the effects of a completely different type of plasma physics. The intracluster medium is a unique environment. It's a collisionless plasma, meaning the particles are so spread out they rarely actually bump into each other. In such a medium, instabilities and phenomena can occur that are impossible to replicate in our laboratories on Earth. The filaments might be the visible manifestation of these poorly understood plasma processes, where energy is transferred and dissipated in ways that our current equations cannot perfectly capture. The significance of these coronal gas filaments, therefore, extends far beyond their ghostly beauty. They are natural laboratories for studying fundamental physics in conditions we cannot recreate. By analyzing their thickness, their temperature, and how they connect to different parts of the cluster, we are essentially conducting an experiment on the nature of magnetism and energy transport in the universe's most massive structures. They are the litmus test for our understanding of plasma astrophysics. Every delicate thread is a piece of evidence, a clue left behind by the violent history of the cluster, and a persistent question mark hovering over our models. They remind us that even in the most chaotic and energetic of cosmic environments, there can exist an unexpected and elegant order, woven from forces we are only just beginning to comprehend. Moving from the delicate filaments of hot gas, we plunge now into the very hearts of the Leo cluster's galaxies, where we encounter monsters of a different kind. In several of these island universes, the central supermassive black holes are not just large, they are inexplicably, disproportionately enormous. They are cosmic overweight champions, tipping the scales in a way that breaks the established rules. For decades, astronomers have observed a remarkably tight correlation between the mass of a galaxy's central bulge, the dense central concentration of stars, and the mass of its supermassive black hole. It's a relationship that suggests these two components grew up together, co-evolving over billions of years, with the black hole's appetite somehow regulated by the star-forming activity of the galaxy itself. It's a fundamental rule of cosmic architecture, but here in the Leo cluster, that rulebook is being torn up. We are finding black holes that are simply too big for their galactic homes, like a mansion built on a postage stamp. To understand why this is so startling, consider our own Milky Way. Our galactic center hosts a supermassive black hole named Sagittarius, a star with a mass of about 4 million times that of our Sun. That sounds immense, and it is, but it is perfectly in proportion to the mass of our galaxy's central bulge. Now, imagine a galaxy in the Leo cluster that has a central bulge with, say, 1/10 the mass of the Milky Way's. According to the established correlation, you would expect its central black hole to weigh in at around 400,000 solar masses. Instead, observations reveal a behemoth of 4 billion solar masses, 10,000 times more massive than it should be. This isn't a slight discrepancy, it's a glaring violation of a fundamental law of galaxy formation. How did this black hole become such a glutton, and what stopped the galaxy around it from growing at a similar pace? The dense urban environment of the cluster itself is almost certainly the key to this mystery. Imagine a galaxy falling into the cluster for the first time. As it plunges through the crowded core, it experiences a phenomenon known as ram pressure stripping, where the superheated intracluster plasma acts like a torrential headwind, blowing away the galaxy's cold, star-forming gas. This effectively shuts down the galaxy's ability to create new stars, stunting the growth of its stellar bulge. It's as if the galaxy's body stopped growing during its teenage years. However, the black hole at its center may have already been feasting on gas right up until this violent moment. Even after the gas supply is cut off from the outside, the black hole could continue to consume any remaining internal reservoir of fuel, allowing it to grow even larger while the galaxy itself is frozen in time. The cluster environment in this scenario creates a lopsided evolutionary path where the black hole gets a final, massive meal before the galaxy's growth is permanently stunted. Another compelling theory involves the chaotic merger history of the cluster. In the crowded downtown of the Leo cluster, galaxies frequently interact and merge. When two galaxies collide, their supermassive black holes eventually sink to the new center and can merge themselves, creating a single, even more massive black hole. It is entirely possible that a galaxy could undergo multiple such mergers, each one adding the mass of another black hole to its core, effectively building up a supermassive black hole through a series of corporate takeovers. If, during this process, the galaxy's stars were also being stripped away and scattered by tidal forces from other cluster members, you could end up with a black hole that has grown via mergers residing in a galaxy that has been dieting, its stellar mass whittled down by gravitational harassment. The result is a black hole that is overweight relative to its stripped-down galactic host. A third and more radical idea questions the very nature of black hole growth in the early universe. Perhaps these overmassive black holes are not the product of their current environment, but are instead ancient relics from a time before the cluster even fully formed. In the early, dense universe, it's possible that massive black holes formed directly from the collapse of enormous gas clouds, bypassing the star formation stage entirely. These direct collapse black holes could have been born supermassive, serving as ready-made seeds for the giants we see today. A galaxy hosting such a primordial seed would have a head start, its black hole disproportionately large from the very beginning. Finding these outliers in the Leo cluster could therefore be a glimpse into the unique and violent conditions of the cosmos's first billion years. The cluster has acted as a cosmic museum, preserving these ancient anomalies in its dense grip. These overmassive black holes are more than just rule breakers. They are living fossils challenging our timeline for how quickly such monsters can form, and what processes ultimately govern the relationship between a galaxy and the dark heart that beats within it. Now, let's shift our gaze to a different kind of signal altogether, one that arrives not as a gentle radio whisper or a warm infrared glow, but as a sharp, brilliant flash of high-energy light. Deep within the Leo cluster, orbiting X-ray observatories have mapped the sky and found something deeply puzzling. Brilliant, point-like sources of X-rays scattered seemingly at random, which, when astronomers cross-reference the data with optical telescopes, reveal nothing at all. These are the unidentified X-ray sources, cosmic lighthouses blazing in a sea of high-energy radiation, yet with no visible counterpart to explain their power. They are perfectly precise on an X-ray image, ruling out a diffuse cloud or a large-scale structure. But when you look at the exact same spot with the most powerful optical and infrared telescopes, you find only empty space or, at best, a faint, normal star that couldn't possibly produce such an energetic output. It's as if you were following the sound of a roaring jet engine and found only a hummingbird. The power source is completely mismatched to what you see. To appreciate just how strange this is, consider what typically creates such intense, localized X-ray emissions in the universe. The usual suspects are well known. One common culprit is a binary star system where a dense object like a neutron star or a stellar mass black hole is actively pulling material away from a companion star. As this stolen gas spirals down into an incredibly hot accretion disk around the dense object, it can heat up to millions of degrees, emitting a torrent of X-rays. Another frequent source are the active galactic nuclei. We've discussed supermassive black holes at the centers of galaxies, which can be brilliant X-ray beacons. But in the case of these unidentified sources, there is no visible galaxy at that location and no telltale binary star system that fits the bill. The X-ray signal is strong and clear, but the object producing it is a ghost. This disconnect sends astronomers on a fascinating detective hunt, and the list of prime suspects reads like a catalogue of cosmic exotica. The first and perhaps most compelling candidate is the long-sought intermediate mass black hole. We are very familiar with stellar mass black holes formed from collapsing massive stars and supermassive black holes which anchor galactic centers. But the existence of black holes in between, with masses ranging from a few hundred to a few 100,000 times that of our Sun, has been much harder to confirm. An intermediate mass black hole, drifting alone in the dark intergalactic space of the cluster, could be the perfect explanation. If it were to occasionally capture and tear apart a passing star or slowly accrete gas from the intracluster medium, the resulting flare of X-rays would be exactly the kind of brilliant, point-like signal we see. Its isolated location would explain why there's no bright galaxy surrounding it, solving the mystery of the missing visible counterpart. Another tantalizing possibility involves quasi-stellar objects or quasars, but with a twist. A quasar is the intensely bright nucleus of a distant galaxy, powered by a supermassive black hole, so luminous it can outshine the entire galaxy around it. Normally, we see these at tremendous cosmological distances. However, it's possible that some of these unidentified X-ray sources are actually background quasars, located far beyond the Leo cluster itself, that just happen to appear projected against it from our vantage point on Earth. While this is a plausible explanation for some of the sources, statistical analysis suggests there shouldn't be so many of them randomly aligned with the cluster. If the number of these point sources exceeds what we'd expect from chance alignments, then we are forced to conclude that a significant population of them are truly within the Leo cluster, making the background quasar theory insufficient on its own. This leads to the most speculative and thrilling category of explanation, that we are seeing an entirely new class of celestial body. Perhaps these are magnetas, highly magnetized neutron stars, but born in environments or with properties so extreme their behavior is unlike anything in our own galaxy. Or maybe they are the signatures of annihilating dark matter particles. While this is a long shot, some theories suggest that if dark matter is made of certain types of particles, they could accumulate in the dense gravitational wells of the cluster and occasionally collide and annihilate each other, releasing a burst of energy that could include X-rays. While the signal from such an event would likely be more diffuse, a dense clump of dark matter could potentially mimic a point source. The very fact that such exotic ideas are on the table shows just how perplexing these brilliant, isolated X-ray flashes truly are. They are celestial enigmas, each one a potential doorway to a new chapter in astrophysics, challenging us to reconsider what kinds of objects can exist in the vast and hidden stretches of cosmic space. But the mysteries within the Leo cluster are not confined to the light its own objects emit. Some of its most profound secrets are revealed by the way it warps the very light from galaxies far beyond its borders. This brings us to the cosmic magic trick of gravitational lensing. According to Einstein's theory of general relativity, a massive object like a galaxy cluster warps the fabric of space-time around it. When light from a distant background galaxy travels through this warped space, its path is bent, much like a lens bending light. The result is that we see multiple, distorted, or magnified images of that single background galaxy, creating stunning cosmic mirages known as Einstein rings or arcs. Gravitational lensing is one of astronomy's most powerful tools, allowing us to literally weigh the cluster by measuring how severely it distorts the light passing through it. In the Leo cluster, however, this reliable cosmic scale appears to be malfunctioning. When astronomers meticulously map the distribution of visible matter, the thousands of galaxies and the glowing hot gas, and then combine that with our standard model for dark matter, they can predict how the lensed background galaxies should appear. But the reality observed through powerful telescopes like the Hubble doesn't match the prediction. The lensing effect is often stronger or has a different pattern than our models suggest. It's as if we're trying to understand the shape of a magnifying glass by looking at the distorted image it creates, only to find that the glass itself must have a more complex and lumpy shape than we can see. The gravity doing the lensing implies the presence of more mass or mass distributed in a stranger way than our inventory of the cluster can account for. This discrepancy forces a fundamental and thrilling confrontation between two possibilities, each of which would reshape our understanding of physics. The first and most widely explored idea is that our model of dark matter is incomplete. Our standard cosmological model, known as lambda CDM, assumes dark matter is cold, meaning its particles move slowly, and collisionless, meaning they pass through each other and normal matter without interacting. This model predicts that dark matter should form a smooth, diffuse halo around the cluster with a dense center and a specific distribution of smaller clumps within it. The anomalous lensing in Leo suggests this dark matter halo might be more granular or concentrated in certain areas than the smooth model allows. Perhaps dark matter particles do interact with each other through some unknown force, causing them to clump differently. Or maybe dark matter comes in different varieties, and the Leo cluster has a unique mix that affects its large-scale structure. The lensing anomalies are a direct probe into the very nature of this mysterious substance that makes up 85% of the universe's matter. The second and far more radical explanation is that we don't need dark matter at all, that instead our theory of gravity itself is wrong. This is the premise of theories like modified Newtonian dynamics or MUN. Proponents of MUN suggest that the effects we attribute to dark matter are actually a sign that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies and within galaxy clusters. In this view, the anomalous lensing in the Leo cluster isn't a sign of missing mass. It's a sign that Einstein's general relativity, while spectacularly successful in our solar system, needs a tweak to work correctly on the largest cosmic scales. The gravitational lens becomes a laboratory for testing the laws of physics themselves. If MUN were correct, it would predict a specific relationship between the visible mass and the lensing strength that could be checked against the observations in Leo, providing a clear, albeit controversial, alternative to the dark matter paradigm. Deciphering which of these paths is correct requires incredibly precise observations. Astronomers don't just look at one lensed galaxy. They use a technique called weak gravitational lensing, which analyzes the subtle, coherent distortions in the shapes of thousands of faint background galaxies. This statistical approach allows them to create a detailed mass map of the entire cluster, revealing the gravitational topography of its dark matter halo in exquisite detail. When they compare this mass map to the map of visible light and X-ray gas in the Leo cluster, the misalignments and unexpected concentrations become starkly apparent. Some subregions of the cluster appear to have far more gravitational pull than their visible content would suggest, as if massive, invisible clouds are drifting through the cluster, warping space-time without emitting a single photon of light. The implications of solving this mystery are monumental. If the lensing anomalies point to a new property of dark matter, we would be on the verge of a breakthrough in particle physics, potentially identifying a fundamental component of the universe that has eluded us for nearly a century. If, on the other hand, they force a modification of gravity, we would be witnessing a scientific revolution on par with the shift from Newton to Einstein, fundamentally rewriting the rules that govern cosmic structure. The distorted images of distant galaxies in the Leo cluster are more than just pretty pictures. They are messages from the edge of our understanding, written in the bent language of light, challenging us to see the true, hidden architecture of the cosmos. Yet another layer of this cosmic mystery lies not in the serene center, but out in the tumultuous frontiers of the cluster itself. Far from the dense core of galaxies, embedded in the faint and much cooler outskirts, astronomers have found colossal scars etched across the sky. These are the radio relics, vast arc-shaped structures of synchrotron emission, so immense they dwarf even the giant radio halo at the cluster's heart. Picture them as faint, ghostly ribbons curved like the bow waves of a ship, but on a scale where the ship is an entire galaxy group and the ocean is the fabric of space. They are the aftermath of the most violent events in the universe, the cosmic equivalent of a sonic boom frozen in time and stretched across millions of light years. The story of their formation is written in the language of shock waves. The leading theory is that these relics are the direct result of colossal mergers between entire subclusters within Leo. When these gigantic structures, each containing hundreds of galaxies and their own massive dark matter halos, slam into one another, they don't just create a simple splash. The collision sends immense pressure waves racing outwards through the thin intracluster medium at speeds of thousands of kilometers per second. These are shock waves of unbelievable power, and as they propagate, they act like natural particle accelerators, far more powerful than anything we could ever build on Earth. They sweep up charged particles, primarily electrons, and fling them to velocities agonizingly close to the speed of light. When these ultra-relativistic electrons then encounter the weak magnetic fields that are woven through intergalactic space, they are forced to spiral around the magnetic field lines, and in doing so, they give off the very radio waves that we detect as these immense glowing arcs. This basic picture seems straightforward, but the reality observed in the Leo cluster presents three profound and interlinked puzzles that leave scientists searching for answers. The first mystery is one of sheer coherence. How does a structure that spans millions of light years maintain such a clean, sharp, and beautifully curved shape? The turbulent environment of a cluster merger should be chaotic like a stormy sea, yet these relics appear as organized and defined as a single, perfect wave. The forces that create them ought to also tear them apart, yet they persist with a structural integrity that defies easy explanation. It suggests that the shock waves themselves must be remarkably planar and uniform, propagating through the cluster outskirts in a surprisingly orderly fashion, a level of organization that is difficult to replicate in even our most sophisticated computer simulations. The second enigma is the source of the electrons themselves. The shock wave can accelerate particles, but it needs a source of particles to accelerate. The primordial electrons that were present in the intracluster medium from the beginning of the cluster's history should have lost all their energy to radiation billions of years ago. They are simply too old and too cold to be re-energized into the powerful glow we see. So, where do these fresh, high-energy electrons come from? One possibility is that the shock wave is actually re-accelerating a pre-existing population of mildly relativistic electrons left over from earlier, smaller mergers or from the jets of active galaxies. It's as if the shock wave is stirring the embers of an old fire back into a brilliant flame. Another, more exotic, idea posits that the shock wave itself can generate the electrons from scratch through complex plasma processes that we are only beginning to understand, potentially creating the very particles it then accelerates. The third and perhaps most baffling puzzle is the incredible longevity of these relics. The high-energy electrons that create the synchrotron glow should radiate away their energy over a relatively short period, cosmically speaking, on the order of 100 million years. After that, the radio relic should simply fade into darkness. The fact that we see them at all means we are likely catching them in a relatively short-lived phase of their existence. However, their precise brightness and structure suggest they have been shining for a significant fraction of the cluster's age, which creates a timing problem. It implies that either the merger that created them happened very recently, which might conflict with other evidence about the cluster's state, or there is a continuous, ongoing process that is somehow re-energizing the electrons within the relic structure long after the initial shock wave has passed, a phenomenon for which we have no clear mechanism. These radio relics are therefore more than just spectacular cosmic landmarks. They are fossilized records of the cluster's most violent history. Their location on the outskirts tells us exactly where a titanic collision occurred billions of years ago. Their size and curvature reveal the energy and geometry of that impact, but their very existence, their pristine form and enduring glow, challenges our grasp of fundamental plasma physics and particle acceleration in the most extreme environments the universe has to offer. They stand as silent, immense monuments to the forces that built the cosmic structures we see today, while simultaneously guarding the secrets of how those forces truly operate on a scale that defies human imagination. Now we turn our attention to a splash of unexpected color in the cosmic metropolis, a vibrant population of young, blue dwarf galaxies that seem to be thriving against all odds. In the dense, violent environment of a massive cluster like Leo, the general rule is that star formation gets shut down. Galaxies are supposed to run out of fuel, their gas stripped away by the intense pressure of the hot intracluster plasma, leaving them to age into passive red systems. This process, known as environmental quenching, should be especially effective for small, fragile dwarf galaxies. They simply don't have the gravitational muscle to hold onto their gas reserves when plunging through the cluster's core. So, the discovery of a significant surplus of these blue, star-forming dwarfs in Leo is like finding a lush, thriving garden in the middle of a harsh desert. It defies the established environmental rules and demands an explanation. The key to their defiance lies in their brilliant blue hue. In astronomy, color is a direct indicator of a galaxy's stellar population. Red galaxies are dominated by older, cooler stars, their vibrant blue, massive stars long since burned out in spectacular supernova. A blue galaxy, by contrast, is a sign of youth and vitality. It means recent, ongoing star formation is taking place, with plenty of massive, hot, blue stars lighting up the scene. For these blue dwarfs to exist, they must have a steady supply of cold, dense gas, the raw material for building new stars. The central mystery, then, is straightforward. How have these diminutive galaxies managed to protect their precious gas reservoirs in an environment that is actively hostile to them? Where is this star-forming fuel coming from? One leading theory suggests these galaxies are not long-term residents of the cluster's brutal core, but rather they are newcomers on an infall trajectory. Picture a dwarf galaxy residing peacefully in the quiet outskirts of the cluster, or perhaps in a nearby filament of the cosmic web, still rich with its primordial gas. As the cluster's immense gravity begins to pull it in, the galaxy makes its first plunge through the cluster's outer regions. During this initial passage, the ram pressure might not be strong enough to instantly strip all of its gas. Instead, the sudden compression as it enters the denser intracluster medium could actually trigger a burst of star formation, causing the galaxy to light up in a brilliant blue starburst just as it arrives. We are, in effect, catching these galaxies at a very specific and short-lived moment in their life cycle, the point of first infall, where they are putting on a final, glorious fireworks display before the cluster environment eventually quenches them, turning them red over billions of years. A second, equally compelling idea proposes that location is everything. Perhaps these blue dwarfs are not on chaotic orbits that take them through the cluster's searing hot center, but are instead on long, looping paths that keep them predominantly in the cluster's cooler, less dense outskirts. In these galactic suburbs, the pressure of the intracluster plasma is significantly lower. A dwarf galaxy orbiting here could potentially hold onto its gas for much longer, allowing for a more extended and sustainable period of star formation rather than a single dramatic burst. Their survival would be a matter of celestial geography, finding a safe harbor within the vast cluster where the environmental forces are less extreme, effectively letting them live a quieter, more isolated life while still being gravitationally bound to the larger structure. But perhaps the most fascinating theory involves a process known as harassment. In the crowded core of the cluster, galaxies constantly whiz past each other. While a single, high-speed encounter might not strip a galaxy completely, the cumulative effect of thousands of these gentle gravitational tugs over billions of years, a process called galaxy harassment, can slowly heat up the stars and gas within a dwarf galaxy, preventing the gas from cooling and collapsing to form stars. However, for some dwarfs, this same process might have the opposite effect. A particularly close gravitational encounter with a larger galaxy could compress the dwarf's gas clouds just enough to trigger a wave of new star formation. In this scenario, the very mechanism that usually suppresses star formation could, under the right conditions, be its unlikely catalyst, creating a brief blue resurgence in an otherwise doomed system. Each of these theories paints a different portrait of the life of a dwarf galaxy within a colossal cluster. The infall model suggests we are witnessing a brief, final blaze of glory. The safe harbor theory implies a strategy of cosmic avoidance, a way to survive by staying on the fringes. The harassment-triggered starburst presents a more chaotic picture, where star formation is sparked by the very violence that should suppress it. The presence of this blue dwarf surplus forces astronomers to refine their models of galaxy evolution, acknowledging that the path from blue to red is not a simple one-way street. It's a complex journey filled with resurgences, delays, and moments of unexpected beauty, reminding us that even in the most regulated of cosmic environments, life finds a way to burst through. As we pull our gaze back from individual galaxies and their supermassive hearts, we encounter a phenomenon that illuminates the spaces between them, a cosmic fog of forgotten suns. Throughout the Leo cluster, a faint, pervasive glow softly emanates from the darkness, a light not tied to any single galaxy. This is the intracluster light, the collective radiance of countless billions of stars that have been ripped from their galactic homes and now drift forever in the isolated vastness of intergalactic space. It is the ghostly residue of the cluster's violent past, a luminous archive written in starlight, recording every collision, every close encounter, and every act of galactic cannibalism that has ever occurred. Yet, when astronomers compare the actual glow of this stellar fog in Leo to the predictions of supercomputer simulations, the two don't match. The real intracluster light is both brighter and more structured than it should be, revealing a history written in far more dramatic strokes than our models can account for. To grasp the paradox, you first have to understand how this light is supposed to form. In the standard picture of cluster evolution, galaxies interact gravitationally as they orbit the cluster's center. When two galaxies pass near each other, their immense gravitational fields tug and pull, drawing out long streamers of stars in a process called tidal stripping. It's a slow, methodical dismantling. Over billions of years, these stripped stars, each one a sun like our own, possibly with its own family of planets, accumulate in the spaces between galaxies, forming a faint, diffuse background glow. Our most sophisticated simulations of this process, which model the gravitational dance of thousands of galaxies over the entire age of the universe, predict that this intracluster light should be relatively smooth and evenly distributed, a gentle haze permeating the cluster. It should be the quiet, predictable outcome of a long and steady evolution. But the Leo cluster tells a different story. Observations from the most sensitive telescopes reveal an intracluster light that is anything but a uniform haze. Instead, it is clumpy and filamentary, shot through with faint ribbons, swirling plumes, and large, asymmetrical blobs of starlight. This intricate structure is a direct challenge to the calm and orderly narrative. Such complex features are the unmistakable signatures of single, catastrophic events, not a slow accumulation of small disturbances. It's the difference between a beach slowly eroded by the tide and a coastline radically reshaped by a single, massive hurricane. The brightness of the glow is another piece of the puzzle. There is simply more of this free-floating starlight than the simulations predict, implying that the process of stripping stars from galaxies has been far more efficient and violent than we believed. This evidence points compellingly toward a history dominated by a few colossal mergers rather than many small interactions. Imagine the scene not as a gentle waltz but as a cosmic demolition derby. In one likely scenario, a large group of galaxies, a subcluster in its own right, fell into the nascent Leo cluster and plowed directly through its core. The gravitational chaos of such an event would have been immense, violently shaking every galaxy in the vicinity and ruthlessly stripping stars from their outer halos in one fell swoop. This single traumatic encounter could have injected a massive amount of stellar material into the intracluster medium all at once, creating the bright, lumpy structures we see today. The simulations that fail to match the observations may be underestimating the sheer destructive power of these rare, head-on collisions between galactic groups. A second possibility involves the specific types of galaxies that fell victim to this process. Our models might be wrong about how easily a galaxy surrenders its stars. Perhaps the Leo cluster was built from galaxies that were unusually rich in loosely bound stellar halos, making them more susceptible to having their stars stripped away even during less dramatic encounters. Or the cluster's dark matter distribution might be so particular that it funnels galaxies into orbits that maximize tidal forces, creating optimal conditions for stellar stripping. The intricate filaments of intracluster light could then be tracing the orbits of ancient galactic victims, their final paths frozen in this faint, luminous memorial. The light itself becomes a tool for galactic archaeology, allowing us to reconstruct events that occurred billions of years ago, long after the galaxies involved have settled into their final, quiet forms. The implications of this paradox ripple outward, affecting our entire understanding of how the largest structures in the universe assemble themselves. If the intracluster light is a true record of a more violent past, then the Leo cluster did not grow gently and steadily, but in fits and starts through a series of dramatic, building-wide upheavals. This would mean that the environment within the cluster was, for long periods, far more chaotic and destructive than we thought, accelerating the evolution of its member galaxies by brutally tearing them apart. The forgotten suns that make up this ghostly glow are silent witnesses to this turbulent history, their collective light a testament to the forces that sculpt not just galaxies, but the very space between them. By studying this faintest of glows, we are reading the most dramatic chapters in the cluster's biography, written in a language of stars adrift. We've marveled at ghostly galaxies and brilliant X-ray sources, but now we turn to a mystery that strikes at the very inventory of the cosmos, a cosmic accounting era of epic proportions. Across the universe, there exists a fundamental budget of normal matter, the kind that makes up everything we can see and touch: stars, planets, gas, and even ourselves. This is known as baryonic matter, and from studying the afterglow of the Big Bang, scientists have a very precise figure for how much of it the universe should contain. Yet, when astronomers take a meticulous census of the Leo cluster, adding up the mass in all its galaxies, all the hot X-ray emitting gas, and even the faint intracluster light, the numbers come up short, significantly short. A substantial fraction of the cluster's normal matter, the very atoms that should be right there in plain sight, is simply missing. This isn't about dark matter or dark energy. This is about the stuff we're made of, and it seems to have vanished into thin space. The scale of this discrepancy is staggering. Based on our most trusted cosmological observations, we know exactly how much baryonic matter should be present in a structure the size and mass of the Leo cluster. Yet, detailed inventories consistently reveal only about half to two-thirds of the expected amount. It's as if you carefully calculated the total weight of all the ingredients needed to bake a massive cake, but when you put the finished cake on the scale, it weighed only half as much. You'd be left scratching your head, wondering where the rest of the flour, sugar, and eggs had gone. In the cosmic kitchen of the Leo cluster, a huge portion of the baryonic ingredients are unaccounted for. This is the missing baryon problem, and it's a puzzle that extends far beyond this single cluster, hinting at a gap in our understanding of where and how ordinary matter resides in the universe. So, if this matter isn't in the obvious places, the galaxies and the hot cluster gas, where could it possibly be hiding? The most promising suspect is a cosmic web of incredibly faint, diffuse gas known as the warm-hot intergalactic medium, or WIM for short. Theorists suggest that the majority of the universe's missing baryons are tied up in this vast, intricate network of filaments, a spiderweb of matter that connects galaxy clusters like the Leo cluster to the rest of the cosmic structure. This isn't the cool, dense gas that forms stars, nor is it the superheated X-ray bright plasma at the cluster's heart. The WIM is a tenuous, warm soup, heated to temperatures between 100,000 and 10 million degrees, too cool to glow brightly in X-rays like the intracluster medium, but far too hot to be seen in visible or ultraviolet light. The reason this matter is so devilishly difficult to detect lies in its temperature and density. At these warm, hot temperatures, the most common element, hydrogen, is highly ionized, meaning its electrons have been stripped away. This ionized hydrogen produces a very specific but exceedingly faint signature in ultraviolet and soft X-ray light. To spot it, astronomers must use a technique akin to cosmic detective work, looking not for the gas itself but for its shadow. They train powerful telescopes on brilliant, distant sources like quasars, whose light passes through these invisible filaments on its long journey to Earth. As this light travels through the WIM, specific wavelengths are subtly absorbed by the ionized oxygen and other elements within the gas, creating tiny, telltale dips in the quasar spectrum. It's like analyzing the light from a distant lighthouse through a thick, invisible fog. You can't see the fog itself, but you can detect which colors of the beacon's light are being filtered out. While this method has confirmed the existence of the WIM in the vast spaces between clusters, finding it within the dense, complex environment of the Leo cluster itself presents an even greater challenge. The cluster's own brilliant X-ray glow and the tangled web of other signals create a cacophony of background noise that can easily swamp the faint whisper of the warm, hot filaments. It is possible that a significant portion of the Leo cluster's missing baryons are hiding in this form, woven through its outskirts and threading between its galaxies in a low-density haze that has until now evaded our detection. Current and future X-ray observatories, with their unprecedented sensitivity, are specifically designed to hunt for these subtle absorption features, hoping to finally balance the cosmic books and account for every last atom. Solving this puzzle would not only close one of the most significant gaps in our cosmic inventory, but would also validate our entire model of the large-scale structure of the universe, confirming that the majestic cosmic web is not just a theoretical idea, but a physical reality holding the majority of the normal matter in the cosmos. Just when we thought we had a handle on the cluster's large-scale structure, we uncover a subtle but pervasive pattern that hints at a deeper cosmic choreography. Look across the vast expanse of the Leo cluster, and you might expect its thousands of galaxies to be scattered randomly like seeds thrown into the wind. But when astronomers meticulously map their positions and orientations, a curious signal emerges. In certain vast regions, the galaxies show a distinct preference, their spins and elongated shapes subtly aligning with each other and with the large-scale filamentary structure of the cosmos itself. This isn't a perfect, regimented order, but a statistical tendency, a cosmic grain, as if the universe had a preferred direction during the cluster's assembly. This phenomenon, known as anisotropic galaxy distribution, transforms the cluster from a mere collection of objects into a fossilized record of its own dramatic birth. To understand why this alignment is so surprising, consider the classic picture of galaxy formation. The prevailing theory suggests that galaxies form within dark matter halos that collapse from nearly isotropic or uniform initial conditions. The random motions and gravitational interactions during this process should, over billions of years, scramble any initial preferred direction, leaving galaxies oriented in a completely random fashion. Finding a distinct, coherent pattern in their distribution is like stirring a cup of coffee for ages and then finding that the molecules have somehow lined up. It suggests that the forces that built the Leo cluster were not entirely random. They carried a directional memory from the earliest moments of the universe, a memory that has been preserved against all odds. The most compelling explanation for this cosmic fossil record points directly to the role of the cosmic web. The universe isn't a uniform soup, it's a vast network of filaments, immense, thread-like structures of dark matter and gas that connect clusters at their intersections like glittering beads on a string. The Leo cluster itself sits at one of these mighty junctions. The theory posits that as matter flowed into the cluster along these specific cosmic highways, it didn't arrive from all directions equally. This structured infall would have imprinted a specific geometry on the forming cluster. Galaxies that assembled from gas flowing along a particular filament would have inherited its spin direction, their angular momentum dictated by the large-scale tidal forces of the surrounding cosmic structure. In this view, the alignments we see today are the preserved trajectories of those ancient rivers of matter, a ghostly map of the channels that fed the growing cluster billions of years ago. But the cosmic web isn't the only actor on this grand stage. Another powerful force that could be shaping this anisotropy is the influence of the cluster's own dark matter halo. The halo is not a perfect sphere, it is triaxial, shaped more like a gigantic, invisible potato. Its complex gravitational field exerts a persistent, directional pull on the member galaxies, a process known as tidal torque. Over eons, this relentless force can slowly nudge galaxies, forcing their orbits and even their intrinsic spins to align with the principal axis of the dark matter halo. It's a slow, cosmic dance where the galaxies gradually fall into step with the music of the invisible mass that dominates their environment. The alignments we observe could therefore be a direct readout of the hidden shape of the cluster's gravitational heart, offering us a unique way to probe the geometry of dark matter itself. The implications of solving this mystery reach far beyond the Leo cluster. If these alignments are indeed a pristine fossil from the cluster's formation, they provide a powerful test for our models of cosmic inflation and the initial conditions of the universe. The specific patterns could reveal the spectrum of the primordial density fluctuations that seeded all structure, acting as a cosmic thermometer for the infant universe. Conversely, if the alignments are primarily driven by ongoing environmental effects like the tidal field, it forces us to rethink the resilience and evolution of galaxies within clusters, revealing how these vast environments continue to sculpt their inhabitants over cosmic time. The anisotropic distribution of galaxies is more than just a curious pattern. It is a sophisticated language written in the orientation of star systems that tells the epic story of how the largest structures in the universe were built, from their primordial origins to their mature present. While we've been charting the grand, enduring structures of the cluster, from colossal radio halos to immense dark matter halos, there exists an entirely different class of mystery in the Leo cluster, one that appears and vanishes in the literal blink of a cosmic eye. Across its vast expanse, automated sky surveys have recorded sudden, brilliant flashes of visible light that ignite without warning and then fade back into darkness, sometimes in a matter of hours or days. These are not the predictable, well-catalogued events like supernova, which brighten and decay over weeks, or the frequent flares from restless young stars. These transient optical events are brilliant, enigmatic, and frustratingly brief, appearing on our digital sky maps like unannounced guests at a cosmic gala, only to disappear before we can properly introduce ourselves. The defining characteristic of these flashes is their profound mismatch with any known profile. When a massive star reaches the end of its life and explodes as a supernova, it follows a very specific script. There's a predictable rise to peak brightness as the shockwave heats the ejected material, followed by a slow, gradual decay as radioactive elements forged in the blast decay and release energy. The light curves of these Leo cluster transients look nothing like this. They are all spike and no tail, often reaching their maximum brilliance startlingly fast and then vanishing just as quickly. Similarly, they are ruled out as common flare stars, while a red dwarf star can unleash a titanic flare, doubling its brightness in minutes. Such flares are emitted across the entire electromagnetic spectrum, from radio waves to X-rays. Follow-up observations of these Leo events, however, frequently find the radio and X-ray bands silent. The energy is channeled almost exclusively into that one fleeting burst of visible light, a bizarre and inefficient conversion that leaves astrophysicists puzzled. This dead end with conventional explanations forces astronomers to consider a roster of far more exotic possibilities. One compelling candidate is a new, entirely theoretical class of stellar explosion. Imagine a scenario where a white dwarf star, the dense, Earth-sized cinder of a sun-like star, is pulled into the crushing gravity well of a supermassive black hole. As it swings close, the black hole's immense tidal forces don't just pull on the star. They can violently compress it, heating its material to the point of triggering runaway nuclear fusion on its surface. The result would be a spectacular, surface-level thermonuclear blast that would shine with the brightness of a supernova, but because it's only a surface event and the star is then torn apart or swallowed whole, the light would vanish almost as quickly as it appeared. This would be a supernova in fast forward, a brilliant flash without the lingering afterglow. A second and completely different line of thought points toward the subtle art of gravitational microlensing. This occurs when a dark, compact object like a lone stellar mass black hole, a neutron star, or even a free-floating planet drifts precisely between us and a distant, faint background star. The object's gravity acts as a temporary lens, magnifying the background star's light and causing it to brighten dramatically for a short period. The signature of such an event is a symmetric, smooth rise and fall in brightness. Some of the Leo transients fit this profile perfectly, acting as a powerful tool for discovering this hidden population of dark wanderers. The incredible density of the cluster makes it a perfect hunting ground for these chance alignments. However, the mystery deepens for the transients that don't show this clean, symmetric profile. Their light curves are jagged, asymmetrical, or exhibit strange color changes, suggesting the lens itself might be complex, perhaps a binary black hole system, or a lensing object surrounded by a clumpy cloud of debris, creating a distorted and unpredictable magnification pattern. Then, of course, there is the most speculative, yet intellectually thrilling possibility that must be acknowledged, even if only to underscore the scientific rigor used to dismiss it. Could some tiny fraction of these inexplicable flashes be technosignatures? The idea that an advanced civilization could engineer structures or processes that release immense amounts of optical light for a short duration is for now firmly in the realm of science fiction. Perhaps it's THE Chinese letter emission from a powerful interstellar propulsion system, or the fleeting glare from an engineering project on an unimaginable scale. While this is the least likely explanation and a hypothesis of absolute last resort, its consideration highlights just how thoroughly these events defy natural categorization. The very fact that such a radical idea can be seriously discussed in scientific circles about the Leo cluster transients is a testament to their profoundly puzzling nature. The immense challenge, and thus the true bottleneck in solving this mystery, is time. Modern astronomy operates on a timescale of scheduled telescope time and peer-reviewed proposals, a process that can take months. A transient that lives and dies in 48 hours is a ghost before any large, ground-based telescope can even be slewed into position for a detailed spectral analysis. The key to the future lies in automated, intelligent systems, networks of telescopes that are continuously scanning the sky, and upon detecting a candidate transient, can instantly alert other observatories and autonomously trigger follow-up observations across multiple wavelengths within minutes. Each flash we catch with this level of detail is a potential Rosetta Stone, a single data point that could finally crack the code and reveal whether we are witnessing a new form of stellar death, the dance of dark objects, or something even more extraordinary. These transient events are the universe's pop-up advertisements, and we are only just learning how to read them before they flicker out of existence. After encountering cosmic speedsters and brilliant transient flashes, we arrive at a mystery defined by a profound and unexpected silence. At the very heart of the Leo cluster, where the gravitational pull is strongest and intergalactic gas should be raining down in a torrential downpour, sits the cluster's dominant central galaxy. This should be the scene of the ultimate cosmic feast, a place where the supermassive black hole at the galaxy's core is constantly gorging on the vast reservoir of fuel funneled toward it. We would expect this monster to be an active galactic nucleus in its most spectacular form, blazing with light and spewing jets of plasma hundreds of thousands of light years into space. Yet, when we point our telescopes toward this titan, we find a scene of eerie tranquility. The central black hole is not just quiet, it is unnervingly dormant, a sleeping giant in the middle of the universe's most lavish banquet hall. This cosmic paradox forces us to ask why the most powerful engine in the entire cluster appears to have been switched off. This silence defies a fundamental principle of galaxy cluster ecology. The central galaxy in a massive cluster like Leo isn't just another member. It's a brightest cluster galaxy, a behemoth that has grown to its immense size by consuming its neighbors and drawing in vast streams of intergalactic gas. The process is driven by the cluster's own gravity. As this gas, which can be millions of degrees hot, loses energy, it should cool and flow inward toward the center in a phenomenon known as a cooling flow. Imagine a pot of steaming water on a stove. If you turn off the heat, the steam condenses and falls back into the pot as water. In the same way, the hot intracluster plasma should be cooling, condensing, and providing a steady, dense rain of cold gas directly onto the central black hole. This infalling fuel should ignite the black hole's accretion disk to brilliant temperatures, powering intense radiation and colossal jets. The fact that we don't see this tells us that something is actively interfering with this seemingly inevitable process, preventing the gas from reaching its final destination. The most prominent theory to explain this quiet is a delicate cosmic balancing act known as feedback. In this scenario, the central black hole isn't permanently dormant. It operates in a cycle of brief, violent activity followed by long periods of quiet. The cycle begins when a small amount of gas eventually does manage to fall onto the black hole. Instead of feeding in a steady stream, the black hole consumes this fuel in a sudden, furious burst. This activity doesn't just produce light, it generates tremendous outflows, powerful jets of relativistic particles and winds of hot gas that blast outward from the galactic center. These outflows inject a massive amount of energy and turbulence back into the surrounding intracluster medium. Think of it as a cosmic thermostat. The outburst heats the gas, preventing it from cooling further and falling in. It's as if the black hole, upon getting a small snack, lets out a tremendous belch that blows all the remaining food off the table, shutting down the feast and putting itself back to sleep. This self-regulating loop prevents the black hole from ever becoming a permanently active monster, maintaining the strange quiet we observe. A second, more passive explanation is that the galaxy is simply suffering from extreme fuel starvation, but not for a lack of available gas. The culprit could be the specific dynamics of the cluster's core. While there is plenty of hot gas, it might be too turbulent to settle into a stable, cooling flow. The gentle sloshing of gas from past mergers or the gravitational influence of other galaxies could be stirring the plasma, keeping it agitated and hot. It's the difference between a calm pond where surface water can cool and sink and a turbulent ocean where constant churning keeps the heat distributed. In this chaotic environment, the gas never gets a chance to cool and condense into the dense, cold clouds required to efficiently feed the black hole. The giant is surrounded by food, but it's all pureed and scattered with no way to bring a substantial portion to its mouth. There is also a fascinating possibility that we are witnessing the aftermath of a recent single event that cleared out the galactic core. A major merger, while not disrupting the entire cluster, could have violently disturbed the central galaxy's gas reservoir. The gravitational turmoil of such an encounter can fling gas out into the far reaches of the galaxy or even eject it entirely, leaving the central black hole with nothing left to consume. Following this catastrophic clearance, it would take hundreds of millions of years for new gas to settle back into the center, creating an extended period of quiescence. We might simply be observing the black hole during this long recovery phase, a temporary silence in an otherwise active life. Each of these theories presents a different vision of the cluster's core, one of a finely tuned self-regulating system, one of a dynamically starved environment, or one recovering from a singular act of galactic violence. The unusual quiet of the central galaxy is not an absence of drama, but a clue to the powerful, invisible forces that govern the energy balance of the entire cluster. Now we encounter a mystery that strikes at the very heart of how we model the invisible universe. For decades, our most successful cosmological simulations have made a very specific prediction about the distribution of dark matter within individual galaxies. This prediction is known as the cusp. Imagine a galaxy's dark matter halo not as a fuzzy, uniform ball, but as a mountain with an incredibly steep, densely packed peak right at the center. According to the cold, collisionless dark matter model, gravity should have pulled the dark matter particles into this sharp, cusp-like density profile where the concentration of dark matter rises dramatically as you approach the galactic core. It's a fundamental outcome of how gravity acts on this mysterious substance over billions of years, and it's a feature replicated in countless high-resolution computer simulations of cosmic structure formation. But when astronomers turn their telescopes to actual dwarf galaxies within the Leo cluster and measure their internal dynamics, carefully tracking how stars move within them, they find something profoundly different. Instead of that predicted steep cusp, the data consistently reveals a core. Picture that same mountain, but with its peak sheared off and flattened into a wide, gentle plateau. The dark matter density in the center of these galaxies is far lower and more constant than it should be. It doesn't spike toward the center but remains in a shallow, almost uniform distribution. This is the core cusp problem, and it represents one of the most persistent and significant tensions between theoretical prediction and direct astronomical observation. It's as if we had a perfect blueprint for a building, but every time we went out and looked at the actual constructed skyscrapers, we found they had flat, squat roofs instead of the intricate spires the plans called for. This discrepancy forces a critical reevaluation of our assumptions about dark matter itself. The leading hypothesis to explain these flattened cores involves the possibility that dark matter is not entirely collisionless. What if dark matter particles can actually interact with each other through some unknown force apart from gravity? In this self-interacting dark matter scenario, as particles swarm toward the galactic center, they could actually bounce off one another, transferring energy and momentum. This process would effectively smooth out the dense central cusp, redistributing the dark matter and creating the shallower core we observe. It's a bit like trying to pack sand tightly into a container by shaking it. If the sand grains are sticky, they'll form a dense lump, but if they're perfectly smooth and bouncy, they'll settle into a looser, more even distribution. The existence of a core could be the first tangible evidence that dark matter has a rich particle physics nature beyond our current understanding. However, there is a powerful and equally compelling alternative explanation that puts the blame not on dark matter, but on the ordinary baryonic matter we can see. This line of reasoning focuses on the dramatic effects that stars and supernova can have on their galactic environment. Imagine the early history of a dwarf galaxy when it was teeming with young, massive stars. These stars live fast and die young, exploding as supernova in a relentless, coordinated fireworks display. The cumulative energy from these explosions is staggering, and it can generate powerful winds that blast outward from the center of the galaxy. This energetic feedback can literally push against the gravitational pull of the dark matter, stirring it up and sloshing it around. Over billions of years, this constant churning from the inside could gradually drag the dense dark matter cusp outward, effectively heating it and transforming it into a shallower core. In this view, the core isn't a clue about dark matter's intrinsic properties, but rather a fossil record of the galaxy's own violent star-forming youth. The unique environment of the Leo cluster makes it a perfect laboratory to test these competing ideas. If the core cusp problem is due to baryonic feedback, then we would expect to see a correlation between the presence of a core and signs of a galaxy's past star-forming intensity. On the other hand, if self-interacting dark matter is the primary cause, then we might observe these flattened cores even in galaxies that have been quiescent for eons, with no history of vigorous stellar activity to stir things up. Untangling this knot is incredibly difficult because the two effects could be working simultaneously, or one might dominate in certain types of galaxies. The core cusp tension is more than just a technical disagreement between models and data. It is a fundamental question about which forces truly govern the internal structure of galaxies. Are we on the verge of discovering a new fundamental force in the dark sector, or are we simply finally appreciating the profound and lasting impact that the brilliant, short lives of stars have on the invisible scaffolding of the cosmos? The answer, hidden within the gentle orbits of stars in the Leo cluster's smallest galaxies, holds the key to a much deeper understanding of the universe's hidden architecture. Deep within the heart of the Leo cluster, beyond the visible starlight and the radio whispers, our most powerful telescopes have detected a different kind of signal altogether, a torrent of the universe's most energetic light. We are now talking about gamma rays, photons carrying millions of times more energy than those we see with our own eyes. And coming from the cluster's central region, there is a persistent, diffuse glow of this radiation that is far more intense than our best models predict. This is the high-energy gamma-ray excess, a mysterious surplus of raw power that hints at processes we have yet to fully comprehend, involving either known physics pushed to its extremes or something entirely new lurking in the darkness. To understand why this gamma-ray surplus is so puzzling, we need to consider what normally produces such intense radiation. Gamma rays are the signature of the universe's most violent and high-energy phenomena. They are generated in the furious accretion disks around supermassive black holes, in the relativistic jets they spew forth, and in the aftermath of colossal supernova explosions. Cosmic rays, protons, and atomic nuclei traveling at nearly the speed of light can also collide with the nuclei of atoms in the interstellar gas, creating a shower of secondary particles, including pions, which then decay to produce gamma rays. This is a well-understood process. The problem in the Leo cluster is that when astronomers add up the expected gamma ray contributions from all the known sources, the active galaxies, the supernova remnants, the collective output of countless stellar systems, the total falls significantly short. There is a glaring, energetic gap between what we can account for and what we actually observe. It's like calculating the total wattage of every light bulb in a city and finding that the city is inexplicably glowing as brightly as the sun. This discrepancy has propelled scientists to explore more exotic explanations, and the most tantalizing of these points directly to the elusive nature of dark matter. One of the leading theoretical candidates for dark matter is a class of particles known as weakly interacting massive particles, or WIMP. According to some models, when two WIMP collide, they could annihilate each other, converting their mass directly into energy according to Einstein's famous equation, and in the process produce a spray of standard model particles, including gamma rays. The dense core of the Leo cluster, with its immense gravitational field, is thought to be one of the best places in the universe to hunt for such a signal. It's a perfect environment for these dark matter particles to be concentrated, increasing the probability of these rare annihilations. The observed gamma ray excess could therefore be the first indirect glimpse of dark matter, the ghostly substance that has shaped the cosmos finally revealing itself through a faint, high-energy spark. However, the dark matter annihilation hypothesis, while thrilling, is far from a settled matter. The challenge lies in the specific characteristics of the gamma ray signal. The energy spectrum of the excess, the precise distribution of its brightness across different energy levels, doesn't perfectly match the predictions of the most popular WIMP models. It's close but not quite right, forcing particle physicists to tweak and adjust their theories, sometimes in ways that feel less than elegant. Furthermore, the spatial distribution of the gamma rays is also a point of contention. If the signal were coming from dark matter annihilation, we would expect it to follow the smooth, spheroidal shape of the cluster's dark matter halo. Some analyses, however, suggest the excess might be slightly more clumpy or extended, hinting that its origin might be tied to a population of visible objects rather than a smooth, invisible field. This leads us to the primary alternative explanation, a vast, unresolved population of mundane but extreme stellar remnants. The universe is teeming with pulsars, rapidly spinning neutron stars that are the dense, city-sized cores left behind after supernova explosions. These cosmic lighthouses generate powerful beams of radiation, including gamma rays, as they rotate. While individual bright pulsars can be identified and their gamma ray flux accounted for, the Leo cluster could be host to thousands upon thousands of fainter, unresolved pulsars. The combined gamma ray output from this hidden population could easily add up to create the apparent excess we observe. It would be like looking at a distant city at night and seeing a uniform glow. You can't make out every single street lamp and window, but you know their collective light is the source. Distinguishing between this pulsar explanation and the dark matter hypothesis is one of the toughest challenges in modern gamma ray astronomy, as the signals can appear remarkably similar with our current instruments. A third and often overlooked possibility involves the intricate dance between cosmic rays and the cluster's own magnetic fields. The Leo cluster is permeated by a complex web of magnetic fields, and it is also flooded with cosmic rays accelerated by shock waves from past mergers and active galactic nuclei. These cosmic rays can become trapped by the magnetic fields, bouncing around for millions of years within the cluster's confines. During this time, their interactions with the ambient light and gas could produce gamma rays through more complex pathways than standard models account for. Perhaps the turbulent history of the cluster has created a perfect pressure cooker for cosmic rays, allowing them to build up to higher densities and energies than we typically assume, leading to an enhanced and unexpected gamma-ray glow from processes we understand in principle but have underestimated in scale. The resolution to this mystery ultimately lies in improved observational capabilities. Current gamma-ray telescopes, like the Fermi Large Area Telescope, have revealed the excess but lack the angular resolution to pinpoint its exact structure. Is it perfectly smooth, as dark matter would predict, or is it speckled with the faint, combined light of countless pulsars? Future observatories, designed with superior resolution and sensitivity, will be able to look for the telltale flickering or specific energy signatures that would definitively identify a pulsar population. Alternatively, if the signal remains stubbornly smooth and its energy spectrum can be matched to a specific dark matter particle model, it could mark one of the most profound discoveries in the history of science. The high-energy gamma-ray excess is more than just an anomaly. It is a high-stakes puzzle at the intersection of particle physics and astronomy, where the answer could either confirm the existence of a fundamental new component of the universe or reveal a previously unseen aspect of the lives and deaths of stars. Yet another layer of the Leo cluster's mystery challenges a rule that astronomers have relied on for decades, a rule about the very shapes of galaxies and the environments they call home. Throughout the cosmos, a predictable pattern emerges known as the morphology-density relation. It's a simple, almost elegant idea. As you move from the sparse cosmic countryside into the dense urban core of a galaxy cluster, the population of galaxies shifts dramatically. In the quiet outskirts, you find a preponderance of beautiful, star-forming spiral galaxies, like our own Milky Way, with their graceful, winding arms. But in the crowded, violent downtown of a cluster, these delicate spirals are expected to be rare, having long since been transformed into smooth, featureless, and aging elliptical galaxies. It's a cosmic form of peer pressure where the harsh cluster environment literally reshapes its inhabitants, but the Leo cluster, in its characteristic defiance, breaks this rule. Here, a surprising number of spiral galaxies are found thriving in the dense central regions, their delicate structures intact, suggesting the cluster's history may have been far less brutal than we ever imagined. To understand why this is so baffling, we need to look at the standard processes that are supposed to dismantle a spiral galaxy. A spiral is a delicate cosmic machine. Its iconic structure depends on a stable, rotating disk of gas and stars. To form new stars and maintain its arms, it needs a rich supply of cool, dense gas. The core of a massive cluster is the worst possible place for such fragility. Several destructive forces are at work there. The first is ram pressure stripping. Imagine a spiral galaxy plunging through the superheated plasma that fills the cluster at millions of miles per hour. This intracluster medium acts like a torrential, invisible headwind. The force is so immense that it can blow the galaxy's precious star-forming gas clean out of its disk, much like strong wind stripping leaves from a tree. Without this gas, the galaxy can no longer create new stars, and its spiral arms, fed by ongoing star formation, will gradually fade. The second major force is galaxy harassment. In the cluster's dense core, galaxies are constantly whizzing past each other. These high-speed, close encounters deliver a series of gravitational shocks and tidal pulls that can severely disrupt a spiral's delicate disk. Repeated over billions of years, this harassment can randomize the orbits of its stars, destroying the organized rotation that defines a spiral and puffing it up into a more chaotic, rounder elliptical shape. A third process, known as galaxy mergers, is the most dramatic. When two spirals of similar size collide and merge in a slow, violent dance, their structures are completely obliterated, and they coalesce into a single, much larger elliptical galaxy. Given the crowded conditions, we would expect all of these processes to have efficiently transformed any primordial spirals in the Leo cluster's core into ellipticals eons ago. The fact that so many have survived is a direct challenge to this entire narrative. So, what could possibly explain this population of resilient spirals? One compelling theory is that the Leo cluster has had an unusually quiet and gentle dynamical history. Perhaps it did not form through a series of violent, head-on collisions between massive groups, but instead assembled more gradually and peacefully. In this gentle assembly scenario, many of the spiral galaxies we see today could have fallen into the cluster on orbits that are less disruptive. Instead of plunging directly through the turbulent core on radial orbits, they might be on longer, more circular paths that keep them in the intermediate density regions for most of their journey, minimizing their exposure to the most extreme ram pressure and the most frequent close encounters. The cluster's gravitational grip, while immense, may have been applied more like a gradual embrace than a series of violent shoves, allowing these spirals to retain their gas and their structure for far longer than our standard models would allow. Another fascinating possibility is that these surviving spirals are simply the lucky ones that fell in very recently on a cosmic timescale. Galaxy transformation is not instantaneous, it takes time. If a large group of spiral-rich galaxies was captured by the Leo cluster only within the last 1 or 2 billion years, we would now be witnessing them in the brief window after their arrival, but before their transformation is complete. We are catching them in effect with their morphological clocks still ticking. They are showing the first signs of environmental stress. Perhaps their gas reservoirs are being depleted or their star formation is beginning to wane, but their fundamental spiral shape has not yet been erased. This would make the Leo cluster not an eternal gentle giant, but a system we are observing at a very special moment in its evolutionary timeline, a snapshot of a cosmic metamorphosis in progress. There's also a chance that these spirals are inherently tougher than we give them credit for. Perhaps their dark matter halos are particularly massive or their disks are unusually robust, providing them with enough gravitational anchor to withstand the tidal forces of harassment. Or maybe their specific orientation as they move through the intracluster medium plays a role. A galaxy that presents its disk edge onto the direction of motion might experience less effective ram pressure stripping than one that plows in face-on. The very presence of these spiral galaxies in the cluster's heart forces us to move beyond simple rules and consider a more complex, nuanced view of galactic evolution, where a galaxy's survival depends on a delicate interplay of its intrinsic properties, its orbital history, and the specific, perhaps unique, temperament of the cluster it calls home. Yet another signal from the Leo cluster defies easy explanation. This one so fleeting and powerful it seems to pluck at the very fabric of space-time. We now enter the realm of fast radio bursts, or FRB. These are not gentle glows or sustained hums. They are cosmic gunshots, bursts of radio waves that release more energy in a single millisecond than our sun does in 80 years. They appear as sudden, brilliant spikes on radio telescopes, and for years most were considered distant phantoms, originating from galaxies billions of light years away. The controversy in the Leo cluster erupted when several of these bursts were detected with a localization so precise it seemed to place their origin points not in the far distant universe, but right here within the cluster itself. If confirmed, this would mean these incomprehensibly powerful explosions are happening not just far away, but in our own cosmic backyard, challenging everything we thought we knew about what could possibly create them. The sheer power of an FRB is difficult to overstate. To generate such an intense, short-duration flash across radio frequencies requires an engine of almost unimaginable violence. The leading candidate for at least some FRBs is a type of neutron star known as a magnetar. Imagine the core of a massive star collapsed into a city-sized ball so dense that a single teaspoon of it would weigh billions of tons. Now take that object and imbue it with a magnetic field 1,000 trillion times stronger than Earth's. This is a magnetar, a cosmic magnet of ludicrous strength. The theory suggests that these magnets can occasionally undergo starquakes, sudden shifts in their rigid crust, that release titanic amounts of energy, snapping their magnetic field lines and unleashing a blast of radio waves that we see as a fast radio burst. It's a compelling idea, and we've even detected an FRB from a magnetar within our own Milky Way, seemingly confirming the connection. But the magnetars we know about in our galaxy produce FRBs that are puny compared to the colossal blasts seen from distant galaxies. If the Leo cluster bursts are indeed local, the question becomes, are its magnetars somehow supercharged, or are we witnessing an entirely different, even more powerful phenomenon masquerading as an FRB? This leads to the intense debate surrounding the Leo cluster detections. The central issue is one of triangulation and distance. Pinpointing the exact origin of an FRB is incredibly difficult. It relies on a technique where multiple radio telescopes across the globe work together to form a single, giant virtual instrument, allowing for extremely precise localization. Some analyses of bursts seemingly from the direction of Leo suggest their dispersion measure, a telltale fingerprint of how much intergalactic material the signal has traveled through, is lower than expected for a truly distant source. This lower value is consistent with the signal having passed through only the Leo cluster's own intracluster medium, and then a relatively short stretch of intergalactic space to reach us, implying the source is within the cluster. If true, it forces a radical rethinking of the energy scale involved. An FRB inside the Leo cluster would still be extragalactic, but it would be far closer than the typical FRB host galaxy. This proximity means it wouldn't need to be quite as insanely powerful to appear as bright as it does from Earth, potentially allowing for a slightly less extreme, but still utterly formidable source. Yet the local hypothesis is far from settled. Skeptics argue that what we interpret as a low dispersion measure could be a misleading artifact. Perhaps the signal from a far more distant galaxy simply passed through an unusually dense filament of the cosmic web or a foreground cloud of gas that we haven't mapped, which mimicked the signature of a closer source. The crowded region of the Leo cluster, with its complex gaseous structures, could be creating this exact kind of illusion, fooling our instruments into thinking the burst is a local event. The controversy highlights the cutting edge of this science. We are pushing our methods to their absolute limits, and every new detection has the potential to either solidify or shatter our assumptions. The debate isn't just about a few data points, it's about calibrating our entire understanding of these mysterious events. If the association is real, the implications are profound. It would mean the Leo cluster is a natural factory for these extreme transient events. This would instantly make it one of the most important laboratories in the universe for studying FRBs. Instead of searching the vast, distant cosmos for these millisecond flashes, astronomers could focus a huge array of telescopes on the cluster, monitoring its galaxies for recurring bursts or other associated signals. A confirmed local FRB would allow us to tie the event to a specific environment, perhaps a region of intense star formation known to produce magnetars, or even to a specific, unusual galaxy within the cluster. We could search for afterglows in other wavelengths, like X-rays or visible light, which fade too quickly to be seen in distant FRBs but might be detectable from a closer source. This would open a window into the heart of the explosion itself, revealing the physics of the central engine in unprecedented detail. Beyond magnetars, a local FRB in Leo would force us to seriously consider more exotic possibilities. Could these bursts be the final death cries of stars being shredded by intermediate mass black holes? Or are they the signatures of cosmic strings, hypothetical, topological defects in the fabric of space-time vibrating and releasing energy? Perhaps they are even linked to the dense, dark matter-rich environments of galaxy clusters, a byproduct of some unknown interaction within the hidden majority of the universe's mass. The simple act of confirming that a fast radio burst originated within the Leo cluster would transform it from a distant curiosity into a nearby, accessible, and deeply personal mystery. It would tell us that the universe's most violent, fleeting explosions are not just phenomena of the far-off depths, but can happen in the colossal cities of galaxies relatively close to home, reminding us once again that the cosmos reserves its most spectacular displays for the most unexpected of stages. But to truly grasp the limits of our understanding, we must take a final, conceptual leap into the realm of the extremely small, where the fabric of reality itself becomes the subject of speculation. Venture now to the most theoretical frontier of all, where the grand scale of the Leo cluster might be offering us a unique lens on the microscopic structure of spacetime. We are talking about the wildly speculative yet profoundly compelling idea of quantum foam. This isn't a substance you could touch or measure with any conventional instrument. It's a theoretical concept born from the marriage of general relativity and quantum mechanics. It proposes that at the tiniest imaginable scales, trillions of times smaller than a single atom spacetime is not the smooth, continuous stage Einstein described. Instead, it is thought to be a churning, turbulent sea, a froth of virtual particles popping in and out of existence, with the very geometry of space fluctuating wildly. It would be a fundamental graininess to reality, like the pixelation on a digital screen when you zoom in to the absolute maximum. The audacious proposal is that this universal graininess, if it exists, could have a subtle but cumulative effect on light traveling across cosmic distances. Think of a beam of light from a brilliant, distant quasar that passes directly through the Leo cluster on its multi-billion-year journey to Earth. According to classical physics, that light is a perfect, coherent wave. But if it's traversing a spacetime that is fundamentally foamy at the Planck scale, each photon in that beam would effectively be jostled by the microscopic turbulence. Over the immense distance from the quasar to our telescopes, these tiny, random jitters could add up. Theoretically, this could cause a subtle blurring or a slight scrambling of the light's phase coherence. It would be an effect somewhat analogous to starlight twinkling as it passes through Earth's turbulent atmosphere, but in this case, the atmosphere is the underlying, choppy texture of the universe itself. The Leo cluster, as a massive gravitational lens, provides a unique laboratory for this. The precise, highly magnified images of background galaxies created by the cluster's gravity are exquisitely sensitive to any perturbation. If the spacetime along the light's path is foamy, it could impose a fundamental limit on the sharpness of these gravitational lensing arcs, a limit that cannot be explained by any conventional astronomical effect. Of course, this idea sits squarely at the boundary of established science and theoretical exploration. The primary counter-argument is one of scale. The fluctuations of quantum foam are hypothesized to occur at the Planck length, a scale so inconceivably small that its effects on a photon traveling across a galaxy cluster would be, by most estimates, utterly negligible. It's like suggesting that the microscopic roughness of a single grain of sand on a beach could affect the course of a massive ocean liner miles away. Many physicists argue that any such effect would be washed out and averaged to zero over such vast distances, making it completely undetectable. Furthermore, other, more conventional explanations for any observed image blurring must be ruthlessly eliminated first. Imperfections in our telescopes, the faint, unresolved glow of intracluster stars, the subtle microlensing by dark matter substructure, or even unknown properties of the interstellar medium within our own Milky Way could all mimic the signature we might naively attribute to quantum foam. Proving this speculation would require isolating a signal that has no other possible cause. This is where the promise of future observatories becomes absolutely critical. Our current telescopes, as powerful as they are, likely lack the requisite combination of razor-sharp resolution and immense light-gathering power to even hint at this effect. The next generation of instruments, however, will change the game entirely. Envision the power of the James Webb Space Telescope working in concert with the upcoming Nancy Grace Roman Space Telescope and the immense, ground-based, extremely large telescopes with their advanced adaptive optics systems. Together, they will study gravitational lensing arcs in the Leo cluster with a precision we can barely imagine today. They will measure the sharpness of these cosmic mirages down to a level that begins to probe the theoretical limits set by quantum gravity models. If, after accounting for every possible known source of error, a fundamental, irreducible fuzziness remains in the most distant lensed images, a fuzziness that increases with the distance the light has traveled, it could provide the first tantalizing, indirect evidence that we are brushing up against the grainy texture of spacetime itself. The implications of such a discovery would be nothing short of revolutionary. It would be a direct observational bridge between the cosmic and the quantum, offering a tangible clue to a theory of quantum gravity, the long-sought unification of Einstein's general relativity with the rules of the quantum world. It would suggest that the universe in its entirety is built upon a dynamic, frothing foundation. While the quantum foam speculation remains one of the most uncertain and far-reaching ideas associated with the Leo cluster, its very consideration expands the horizon of what astronomy can aspire to reveal. It transforms the cluster from a mere collection of galaxies into a colossal interferometer, a natural instrument of unparalleled scale, capable of testing the most fundamental properties of reality. As if the cluster's sporadic flashes weren't puzzling enough, our next mystery introduces a beat to the chaos, a cosmic metronome ticking with unimaginable power. Deep within the Leo cluster, X-ray observatories have detected a source that doesn't just flare randomly, it erupts with a startling regularity. These are periodic X-ray flares, brilliant pulses of high-energy light that burst forth from a single point in the sky, fade away, and then, with clockwork precision, return again and again. The periodicity is uncanny, repeating on timescales that can range from a few hours to several months, creating a predictable rhythm in the otherwise unpredictable high-energy symphony of the cluster. This isn't a one-off explosion, it's a repeating signal, a beacon that demands an explanation for its perfect energetic timing. The first and most compelling suspect in this cosmic whodunit is a dance of titans, a binary system of supermassive black holes. Picture two of these monstrous objects, each weighing millions or even billions of times the mass of our Sun, locked in a tight orbital embrace at the center of a merged galaxy. As they circle each other, their immense gravitational fields warp the space around them, creating a complex and violent environment. Now, imagine a vast disk of gas, the leftover debris from the merger, swirling around this binary pair. The gravity of the two black holes would disrupt this disk, clearing a central cavity. However, streams of gas could still be funneled onto each black hole, particularly at specific points in their orbit. When the secondary black hole passes through the densest part of the surrounding gas disk on its elliptical path, it could trigger a sudden, massive influx of material onto its companion or onto itself. This sudden dumping of fuel would ignite a brilliant X-ray flare. Then, the black holes would continue their orbit, only to trigger another identical dump of gas and another flare the next time they return to that same orbital position. The period of the flares would thus be a direct readout of the orbital period of the binary, allowing us to literally clock the motion of these invisible giants. However, fitting this beautiful theory to the observations present some thorny challenges. For the flares to be so sharp and distinct, the orbital environment would need to be incredibly clean and stable. But the region around a supermassive black hole binary is expected to be one of the most chaotic places in the universe, filled with swirling gas, shock waves, and intense radiation. It's difficult to see how such a messy system could produce such a clean, repetitive signal without the flares being smeared out or disrupted. Furthermore, for the shortest periods observed just a few hours, the two black holes would have to be orbiting so close together that general relativity predicts they would merge in a spectacular burst of gravitational waves within a very short time, cosmically speaking. Finding a system with such a short period would be like catching a stellar couple in the final, frantic seconds of their dance before a final, explosive collision, a rare and fleeting sight. This leads us to a second, equally violent explanation, a series of repeated tidal disruption events. We know that when a star wanders too close to a single, isolated supermassive black hole, it can be torn apart in a single, cataclysmic event. But what if the star doesn't get completely consumed on its first pass? Consider a scenario where a star is on a highly elliptical orbit that brings it dangerously close to the black hole at its nearest approach, but not quite close enough to be fully destroyed. On each pericenter passage, the black hole's tides would violently strip away the star's outer layers, pulling a portion of its material into a temporary, searingly hot accretion disk. This stolen gas would then rapidly fall onto the black hole, powering a brilliant X-ray flare. The star would then swing away on its long orbit, only to return years later and have another layer ripped off, triggering another identical flare. In this grimly periodic scenario, the star is being slowly eaten over multiple orbits, and the clock of the flares is set by the orbital period of the doomed star itself. This could explain longer period events on the scale of years that might be difficult to attribute to a tight black hole binary. Yet there are problems with this model too. The process of partial disruption is messy, and it's unlikely that each stellar pass would strip away exactly the same amount of material to produce flares of such consistent brightness. Furthermore, the intense gravitational forces at play would likely alter the star's orbit over time, changing the period between flares, an effect we don't always see in these Leo cluster sources. The clock would be slowly drifting, not ticking with perfect precision. The remarkable regularity of some of these signals pushes us to consider that we might be witnessing something entirely new, a class of periodic high-energy phenomena we haven't yet imagined. Perhaps the engine isn't a star or a binary pair, but an intrinsic instability in the accretion flow itself. Picture a supermassive black hole feeding from a stable, gaseous disk. Under the right conditions of temperature, density, and magnetic field strength, the disk could undergo a cyclical process where it accumulates mass until a critical threshold is reached, at which point it dumps a huge portion of that mass onto the black hole all at once, producing a flare. The disk then resets, begins accumulating mass again, and the cycle repeats. This would be a natural, thermodynamic heartbeat, a pulsation driven by the fundamental physics of how matter falls into the ultimate gravitational well. The profound significance of these periodic flares lies in their potential to become precision tools for astrophysics. If they are from a binary black hole, they provide a direct and relatively simple way to measure the masses and separation of these elusive objects, parameters that are otherwise incredibly difficult to pin down. They offer a glimpse into the final stages of galactic mergers and the future gravitational wave signals that such systems will produce. If they are from a repeating tidal disruption, they open a new window into stellar dynamics in galactic nuclei and the complex process of how black holes feed. And if they represent a new type of accretion instability, they reveal a fundamental aspect of how matter behaves under the most extreme conditions imaginable. Each regular pulse of X-ray light is a coded message, holding within its timing and its energy the secrets of the most powerful engines in the cosmos, challenging us to decipher its rhythm and understand the colossal forces that set its beat. And now we reach the final foundational mystery, one that strikes at the very identity of the cluster's most dominant member. At the heart of the Leo cluster sits a true giant, a galaxy so massive it exerts gravitational sovereignty over all others. For decades, the prevailing theory of how such behemoths grow has been straightforward and brutal galactic cannibalism. The idea is that the central galaxy grows by consuming smaller neighbors, tearing them apart with its immense gravity and absorbing their stars, their gas, and their very essence. We see the evidence for this in the vast tidal streams and the immense halo of the galaxy itself. Yet, when astronomers perform a detailed chemical analysis, a kind of cosmic blood test, on this central giant, the results are bewildering. The elemental abundances within its stars tell a story that doesn't match the simple tale of a voracious predator. The chemical fingerprints are all wrong, suggesting a past far more nuanced and complex than our standard models of hierarchical growth can explain. To understand this chemical paradox, imagine you're an archaeologist studying the history of a great city. You'd expect to find layers of artifacts, each telling you about the different cultures that were absorbed as the empire expanded. In galactic terms, the artifacts are the specific ratios of elements like iron, magnesium, and oxygen found in the stars. Smaller dwarf galaxies, which formed stars quickly and violently in their youth, tend to be rich in alpha elements like oxygen and magnesium, forged in the rapid explosions of massive stars. Larger, more slowly evolving galaxies, like our own Milky Way, show a higher proportion of iron, which is released more gradually over time by Type 1a supernova. The standard cannibalism model predicts that as the central galaxy eats many small dwarfs, its stellar population should reflect that diet, showing a chemical signature dominated by these alpha elements. But the chemical census of the Leo cluster's central galaxy reveals something entirely different. Instead of the alpha element-rich signature of a diet consisting primarily of dwarf galaxies, its stars show a surprisingly high iron content. This is the core of the mystery. It's as if our archaeological dig uncovered a city that, according to historical records, conquered only small, rustic villages, yet its artifacts are overwhelmingly those of a sophisticated, long-lived metropolis. The galaxy's chemical makeup points to a history of forming a large number of its own stars over a very long, extended period, or of merging with other large, chemically mature galaxies, not just snacking on a swarm of small, primitive ones. This forces a profound question. Has this giant been a solitary, monolithic structure for most of its life, growing primarily from within, or did its major growth come from a few rare mergers with other giants? This leads us to the first radical reinterpretation of the cluster's history, the possibility of a few dramatic, dry mergers. In this scenario, the central galaxy didn't grow by steadily consuming gas-rich dwarfs, but by merging with other massive, elliptical galaxies that were already red and dead, devoid of gas and no longer forming stars. Because these large progenitors had themselves evolved for billions of years, they would have built up high levels of iron, and their merger would not have triggered a new wave of star formation that could alter the chemical balance. It would have been a relatively clean fusion of two mature stellar systems. This would explain the high iron abundance without the need for a chaotic history of devouring many small, chemically primitive galaxies. The cluster's core would have been the stage for a few epic collisions between titans, a series of corporate mergers that created a single, vast corporate entity, rather than a slow, predatory consumption of many small businesses. A second, equally compelling theory suggests that the environment within the early Leo cluster was uniquely hostile to dwarf galaxy survival. Perhaps the process of strangulation and harassment we discussed earlier was so efficient that most small galaxies were stripped of their gas and torn apart completely before they could even be consumed by the central galaxy. Their stars would have been scattered into the intracluster light, rather than being neatly absorbed into the giant's halo. In this picture, the central galaxy's growth was stunted early on, and its chemical evolution was largely self-contained, driven by its own internal star formation processes over eons, relatively untouched by the carnage happening around it. The chemical patterns we see today would therefore be a fossil record of its own isolated evolution, not a scrapbook of its meals. the implications of this single chemical anomaly ripple outward, forcing us to reconsider the entire life story of the Leo cluster. If the central galaxy's growth was dominated by a few major mergers, then the cluster itself must have assembled differently than we thought. Instead of a steady, hierarchical buildup from the bottom up, its core may have formed through a top-down process where a few massive building blocks came together first, creating a stable central structure very early in the universe's history. This would dramatically alter our timeline for how quickly such colossal structures can arise. Alternatively, if the galaxy grew in isolation, it suggests the cluster's gravitational dynamics are even more effective at destroying small galaxies than we realized, fundamentally changing our understanding of environmental effects on galactic evolution. The chemical abundance patterns are more than just a data point. They are a profound historical document. They challenge the very narrative of how the largest galaxies in the universe are born, forcing us to choose between a history of epic, monolithic mergers or one of solitary, internal growth against a backdrop of unparalleled cosmic violence. And so, after this incredible journey through the celestial metropolis of the Leo cluster, we're left with a profound sense of awe and humility. We've navigated past a galaxy missing its dark matter ghost, felt the immense whisper of a giant radio halo whose engine remains unknown, and wandered among the phantom population of ultra-diffuse galaxies, cosmic giants holding their fragile forms against all odds. We've traced the razor-sharp edges of cold fronts, baffling thermal boundaries that defy the natural flow of energy, and followed the twisted paths of stellar streams, using them to map the unseen clumps of dark matter that warp the fabric of space itself. We've seen galaxies glowing with a hidden, warm light from a luminous infrared excess, whose source could be anything from a buried stellar baby boom to a feast of primordial black holes, and watched as cosmic speedsters, entire galaxies, were flung outward at impossible velocities, challenging the very gravitational limits of the cluster. We marveled at the delicate, enduring filaments of coronal gas, structures that should have been shredded by turbulence, and confronted the cosmic rule breakers, supermassive black holes that grew inexplicably overweight for their galactic homes. We hunted for the brilliant, unidentified X-ray sources, point-like beacons shining in the darkness with no visible counterpart, and saw how the cluster's own gravitational lens, its ability to bend light, creates anomalies that pit the existence of dark matter against a potential modification of Einstein's theory of gravity. We stood before the colossal radio relics, the fossilized bow shocks of ancient mergers, and celebrated the vibrant surplus of young, blue dwarf galaxies thriving where they should have been quenched. We studied the faint, structured glow of intracluster light, the ghostly residue of forgotten suns that tells a more violent history than our models allow, and grappled with the missing baryon problem, a cosmic accounting error where half the normal matter in the cluster has simply vanished, likely hidden in a faint, warm web of gas. We observed the subtle, anisotropic alignments of galaxies, a fossilized directionality from the cluster's birth, and chased the fleeting, transient optical flashes that ignite and vanish before we can understand them. We pondered the unusual quiet of the central galaxy, a sleeping giant in a hall of plenty, and wrestled with the core cusp problem, where the dark matter in dwarf galaxies refuses to form the dense peaks our simulations demand. We detected the mysterious high-energy gamma-ray excess, a signal that could be the first glimpse of dark matter annihilation or simply the combined glow of countless pulsars. We noted the resilient spiral galaxies defying the morphology-density relation by surviving in the dense urban core, and investigated the controversial fast radio bursts that may be going off in our cosmic backyard. We even ventured into the realm of quantum foam, using the cluster as a colossal lens to potentially probe the grainy texture of spacetime itself. And finally, we clocked the rhythmic, periodic X-ray flares, the heartbeat of a hidden binary monster or a star being slowly devoured over millennia. And we closed by deciphering the paradoxical chemical abundances in the central giant, a story written in starlight that contradicts the simple tale of galactic cannibalism. Together, these 25 phenomena reveal the Leo cluster not as a static collection of islands, but as a dynamic, evolving cosmic laboratory. It is a place where the fundamental laws of physics are not just observed, but are actively tested, challenged, and sometimes broken. Each mystery, from the smallest scale of quantum foam to the largest scale of dark matter halos, is an open question, an invitation for the next generation of thinkers and explorers. The universe, it seems, is far more creative, more bizarre, and more wonderfully mysterious than we ever dared to imagine. Now we turn the discussion over to you. In the comments below, we'd love to hear which of these 25 phenomena captivated your imagination the most. Was it the ghostly galaxy with no dark matter, the rhythmic X-ray heartbeats, or the possibility of feeling the quantum foam of spacetime? Let's continue this conversation, and if you enjoyed this deep dive into the unknown, be sure to subscribe. We have so many more of space's greatest unsolved puzzles to explore together.